Make your way here. Maybe bring your food to sit down and eat while we're presenting. I'll eat one. Zoom is recording. All right. All right, everyone, welcome to the 2025 GAIA competition. Thank you so much for being here. We're very excited to have UCSD team, Cornell team, and our representatives from WBR here, and we're ready to get started. So GAIA was founded around 4 years ago by Becca, Mo, and Mark. Mark and had graduated last year. Mo is no longer at Cornell, and Becca is still our founder, and she's here and the leader of Gaia. Um, so our team was GAIA is a national competition that empowers college teams to conceive, design, prototype, and execute high-impact solutions for global sustainability. And last year we partnered with WindAid. This year we partnered with World Bicycle Relief, and we are so excited that our team has really been able to expand and adopt new teams, make new partnerships, and we're happy to have everyone here. So this year we partnered with World Bicycle Relief, and our teams were designing sensors for these bikes, and we will get into more of the technical aspect of the competition a bit later. This is just a general overview. Welcome, WBR. Would you guys like to wave? Awesome. We're so happy to have you guys here. So this year, this is a couple of team photos of the Gaia organizers. I am the marketing lead. Becca is president and technical lead. Do you know me? AJ is another team lead. And where's Eric? Oh, Eric. All right. So winter 2023 was the first time that we sent Gaia members, organizers to Peru. Mark was one of our founders, and he went to Peru and they built the wind turbines. And we had our Cornell team go also to Peru and implement their wind turbine designs this past summer. And this year we hope to also plan a trip and coordinate to send our competitors abroad. So thank you guys for being here, and we're ready to start the competition. Which one? When on this week? Oh, good. Okay. WBR, if you guys would like to. Did you guys can? Yeah. Okay, I can pull it up.
Got it. Two separate emails, one from Alex's slides, and then I had sent a link to that.
Okay.
Get my big head out.
Okay.
You sent over the document.
It was in that, I think it's just, we, 2024.
Okay. I will restart the sharing. Do you want the video or the slide?
The presentation is very good. Would you
Okay. Yeah, go ahead.
appreciate it? Okay.
You welcome our vendors from World High School.
Do you
Yeah.
Of the organization, and especially about the impact of.
Okay. Well, hello. Hi, I'm Alex. This is my teammate Chris here. We are here from World Bicycle Relief. We came in from Chicago just to spend some time with you guys and talk a little bit about the work that we do, and then sit back and watch and hear about the work that you guys have been doing on the Buffalo Bicycle. We're really excited to be here, and really grateful to the organizers for having us. So thank you very much for welcoming us and inviting us to speak with you a little bit today. So before we get started, Chris and I wanted to spend a little bit of time talking to you about what World Bicycle Relief does, why we use the Buffalo bicycle, where we work, a little bit about our 20-year history. This is our 20th year anniversary, so we're really excited to celebrate it. But really quick, so at World Bicycle Relief, our mission centers around providing bicycles to the individuals, to the people and communities around the world that need them the most, where they're separated by far distances, oftentimes walking on foot to get where they're going. And so we provide life-changing bicycles to those people and those communities in need. A little bit about how our response is shaped. We work directly with the communities that we serve to understand how our solution better fits with the needs of the individual communities. So whether that's bicycles that are being used to access healthcare by community health workers, nurses, economic opportunity for people who are trying to access jobs and marketplaces, or education, students who are trying to get to school. These are some of the key impact areas where we focus these bicycles to get people where they're going, to mobilize the individuals in the most need. It's not just about maintaining bicycles in the hands of people that need them the most. It's about training mechanics locally, as I'm sure you can appreciate, on how to maintain the bikes and keep them operational, keep them sustained. And it's also about supplying a steady flow of spare parts. So having a supply chain that is accessible to people in their communities, that they can stay on their bikes, oftentimes to access livelihoods, healthcare, education, things like that. So I'll give Chris a chance to speak a little bit about the ecosystem that surrounds the bicycle.
Alex alludes to it a little bit already, but World Bicycle Relief is very unique in the approach. A lot of times NGOs will provide things like water, but our particular organization was very focused on the sustainability of what we're trying to achieve, or what the benefit that we're trying to have. So we started out with a bicycle where it was specified with existing bike parts that were available in the markets today. But those type of components really don't hold up in the environment. No one designs for that particular use case. So World Bicycle Relief started designing very purpose designed solutions for the bikes that we're providing. But not only that, you have to think about the bigger ecosystem around it. When you're in Africa, you don't have a big shop around the corner. You don't have anywhere to get spare parts. So we get into the communities. We actually help to train mechanics, so then the mechanic now has a livelihood. They have the ability to go through us. We put shops in those locations to be able to get access to spare parts. That gets the connection to our supply chain. And so, not only are we creating a bicycle, it's very focused on the whole ecosystem around how do you generate the improvement of the whole of the lifestyle of the people that we're trying to serve. So ecosystem is really the key aspect of it. And all of you familiar with bikes, of course, you've had the bikes. You can tell it's not like the bikes that you're riding down the street today. They're very heavy. They're very purpose-built, very steel. We've got a lot of steel, and every little element of a bike is really, really thought through as far as how will you maintain it. How can it be used in many different ways? So having a platform bicycle that can be configured in different ways to meet the needs in different different areas. For example, we work in Colombia as well as Africa. So the needs, how tall people are, whether you're working with children, whether you're working with healthcare people who are carrying people on their bicycles, really thinking about all of those little aspects of the bike into design. So you're not having 16 different bikes that you need to produce. You can have one bike that can be configured many different ways and be maintained very quickly. Is a challenging design problem.
And yet the universal platform that is the Buffalo bicycle
Yeah,
exists.
the new drug training license. It's not something that you would think of or that in general in the biking community here in the States that anyone would think that doesn't make any sense at all. But in the environments that we work in, it's very robust. It's very easy to manufacture and it's very intuitive as far as maintenance goes. And so it's a really great fit for our environment. Where in the cycling community, they're like, why would you do something like that? So it's a really fun challenge and a really great place to be innovative and really think about solving the problem in, the easiest way possible.
A little bit more about the focus that we have and where we're trying to have the most impact with the bicycles that we're distributing in our program. So most of our work is focused around enabling access to these three key impact areas that you see up here: education, healthcare, and economic opportunity. So I'll touch a little bit on some of the things that we've learned working with the communities that we serve to understand after receiving a bicycle or once receiving a bicycle as a primary or a reliable means of transportation, what sort of changes do you see in somebody's life? So for girl students in particular, some of the data that we've gotten back shows a 66% increase in punctuality, meaning the time that a girl's getting to school on time, right? A 28% increase in attendance. That's overall. Now, that's one study that we did within one community that we serve, right? So it can't be taken as an absolute across all of these varying communities and areas where we work, because people's lives are different, right? But when we see 19% decreases in dropout rates in certain communities, we start to get really excited by that kind of stuff. So I won't walk one by one through all of these, but one of the biggest ones, it's kind of blocked here for a sec, is a 33% time savings. And that's one that stands out to me because it's not only for education, you're going to see that show up for all of the other impact areas that we measure. And throughout the next week, throughout the next month, as you're preparing for finals, I want you to spend just a moment thinking about time and how much that time means to you and the value of your time. And some of that time that you spend traveling point A to point B. This one stands out. I know we're in a school, so I'm going to spend a little bit more time talking about education, but a lot of the students that we serve, a lot of the people that are receiving bicycles are trying to get where they need to be, right? And if they're pressured to get there by a certain time, their constraints are oftentimes things that we might not even be considering, right? Limit in the number of options that you have to get where you're going, right? I live in Chicago in a really urban setting where I have like a dozen different transportation means at my disposal at any point in time. Pretty much on my cell phone, between my cell phone and my wallet, I can get on like 10 or 12 different things to get to the grocery store, to get to work, to get to a hospital, to get to school. The other thing to consider is the sun, right? If you live in a place where the power grid, where the lights, the infrastructure that surrounds you doesn't necessarily support travel outside of the hours where it's daylight, you are now constrained by a new variable, right? And so a 33% time savings for people can be life-changing alone, right? When you don't even factor in any of these other things that we're measuring here. So I like to spend a little time on that because it stands out to me and I think it's relatable to anybody in this room, to anybody that I talk to. When you save time, when you save someone time, you give them an ability to do with that time something that they need to do, whether it's pursuing their livelihood, whether it's studying for school, whether it's resting, whether it's doing better work. There's lots of ways that that can be used. So I'll carry on so that we can get to this competition because I'm excited. But some of the other things that we've seen when we talk to people in healthcare specifically, right? An 88% increase in reach for nurses, community health workers who are seeing their patients oftentimes on foot before they receive a bicycle. They're walking to all these households, 10, 12, 20 kilometers. Now they've got a bike to get there. So they're seeing 88% more of their patients. Their workers are staying for longer. They're retaining their workers better. There's an increase in referrals. The emergency use for bicycles as like an ambulance or an emergency transport vehicle goes up. And bicycles become oftentimes the primary mode of transportation for health workers who receive them. And we'll move on here. But again, you'll see a massive time savings for people who are looking for economic opportunity. There's an increase in productivity and boom, big one, 23% increase in income. That's huge. You spend less of your money maintaining your bicycle because it lasts. And the spare parts that you need are there in your marketplace. You don't have to travel to find them. And there's someone who knows how to fix your bike when you need it. But most of the time, you're just making money using your bike to further your business, your livelihood. So there's some really, really cool things that you see when you give somebody mobility, when you help empower them. Some of the places where we work, you'll see at the top here, these 7 countries listed are the places where we have current program countries for World Bicycle Relief. That's where we're funding and distributing bicycles. We're training mechanics, supplying spare parts through brick and mortar retail shops, all the things we've been talking about. You'll also see listed here, pardon me, a number of other countries where the Buffalo Bicycle has reached that extend beyond our network, our infrastructure. That's through the social enterprise that we have that allows us to work with other NGOs. Think UNICEF, Red Cross, Mercy Corps, lots of good ones. I could keep going. Other government institutions, the Ministry of Health, Ministry of Education, when we can show them what happens when you mobilize these communities with bicycles, they oftentimes want to partner with us. So in that way, you can see a spread to other places, other countries, other nations where we've been, where we don't have our program staff today. And then in black at the bottom, you'll see where our fundraising operations are. Got North America covered. And then we're also in Europe, we're in the UK, we're in Australia, we're in Switzerland, we're all over the place. Lastly, so I mentioned earlier, this is our 20th year anniversary. We've been doing this for a little while. We've in that time distributed just shy of 900,000 bicycles. We're somewhere in the ballpark of 875,000. These numbers are a little old, which translates to just over 4 million people empowered. We see that a bicycle doesn't just mobilize one person. It's oftentimes other members of the household, other people in their neighborhood. It's like a 5x multiplier that you see on top of each bike that goes out. So when we think about over 4 million people empowered, we're getting close to 1 million bikes, hopefully by next year. Help us along. You guys are helping us along. We've worked in 21 countries, trained over 3,600 mechanics, and we've built over 100 retail shops. So we've been working really hard. But with the global need for mobility being at over 1 billion people, you'll notice this is not quite 1 billion. I know you guys are math people, right? Like this is not anywhere near. So it's that partnership, that growth that we continue to seek out to help us get the word out, to help prove why bicycles are an effective tool for mobilizing communities and for impacting these other key areas of life. But that's a little bit about us. I could answer way more questions, but I'm going to leave some time for us to talk at the end of the presentation. We're going to be here all day. We've got a short documentary that we want you guys to watch. It specializes a little bit in the newest product development innovation that Chris can talk a little bit more about, but you've been really exposed to hands-on. So I'll shut up and we'll get to it. But thank you guys for listening. If you guys have any questions, please feel free to hold on to those for just a few minutes.
I think the documentary is really interesting. It really does focus on product development. It's a very unique part of our role. So people really think of a bike and it just kind of appears, but understands all the thought, the energy, and manufacturing. So this is really a great opportunity to share that. Okay.
Enjoy.
That's all right. Some sound in particular place. They're in various places. These buffer was the basic something because I had been trying to bring these buffers. You focus on it. First, you must settle. I settle. I don't move very fast. feeling peaceful. This bicycle is steering. This bicycle is strong. I don't use a lot of force. Moving comfortably to my destination.
%70 of the African continent live in a rural setup and have no access to mobility. It is that group of people that we feel have been left behind. One bicycles in the hands of the people who so need them, in terms of the three thematic areas, which is health, livelihoods, and education. Yes, people have walked to school, but it's a challenge. This is something that changes all these children's lives. They're safe, they can get home on time, they can be able to improve the quality of their life, they can actually perform better. So everybody's rushing to this school, number one, to ensure that they have access to this bicycles because it will provide mobility in a household. You find that this school has an enrollment of 500, and all of a sudden it's moved to 1,400 because they're able to get a bicycle. They can change the whole rhetoric of their family.
Zaidi sana watoto wenye wanaenda shule na watoto wenye wajiwezi na wanasoma town. Sasa naona wengine wakina na baiskeli. Sasa nisaidia watoto kwenda shule, professional pia msaidia sana. I normally take the children at school. I am also a business lady. Now when I am going to the student, I can use offer. In only 5 hours, I've already finished my work. And I want to stay vizuri sana because nimefanya every kila watoto wangu wamejua kuendesha. Sasa nalikuwa busy kidogo, nalimwambia chukua baiskeli, yani ungemwambia kitu fulani, na kijana anaruka na baiskeli, anarudi. Sasa nasikia vizuri sana kama unaendesha. The buffalo bike. It means a lot to me because it has already helped me a lot. Watu wakona kama wakona bicycle na wengi, hata kama mimi mwenyewe sijanunua.
To make sure that we get the impact we have profitable bicycles, the social enterprise. So not necessarily just donating the bicycles, but ensuring that we have a thriving set of shops that supply spares for the bicycles that we are distributing. The community has access to these bicycles through the shops that we have. And then we are training mechanics to support the bicycles that are in the market. We're giving them a source of income because more bicycles are out. They will be able to take care of the bicycles. The energy the Buffalo bicycles and World Bicycle Relief bring together is necessary to ensure that what we really make up to do is being done, creating a good bicycle ecosystem in rural areas.
The bikes were insert if we could bring our industry to bear on this serious problem, we could make a really big difference in communities all over. Most of the people we've engaged with in our industry happen to be at the middle to top end of bicycle performance.
I was supportive before program support, but I had a head tilt moment. It was like, this is really what you're gonna do. It's been through FK's influence and passion that he's also engaged a wide swath of the bike industry to support the efforts of World Bicycle League.
Most of what the industry produces will be sport, leisure. That's not to denigrate those activities, but what we need is different. We need a durable, universal mobility tool. It's important to see every step of the process. Only when you have the total overview of every step in the system can you think clearly about what the solutions need to be. It's a simple product conceptually, but executing a bicycle to a consistent quality and affordable cost takes an amazing amount of coordination. There's really no way to do that without the help of other people. Connected. Very little on our bike is off the shelf. Everything's been considered, even down to the finish on the washers, the hardness of the axles, the type of paint finish we use, even the color fastness, graphics, packaging, way we package things. Number of things that have gone into it that make no obvious difference to the product, but produce better outcomes.
See many organizations or development was that they prescribe to the community what they want. I think that's looking at it from the back way. We need to know what does the market require, and then we work towards getting that. So the test riders is extremely important.
We this bicycles. Look at them, if they rank them. For the first time, this is a bicycle which somebody can afford after sale, which is can never happen in Kenya. Test riders, they are giving reports. After 2 weeks, you bring a report. How was the bicycle? How did you use it? What are the challenges? These challenges make the company to modify the bicycle. If someone came to me and said, hey, where would you go for the absolute most talented product development engineers in the world? I'd go, well, Giant, Trek, and Swing.
Engineers that we've trained for years, they've come to be the top of their class and high-end cycling components. They say they want to go work for Little Bicycle. It hurts, but there's nothing you can do but say yes.
Trying to get user feedback. We want it to be as broad as possible. What we get from those field riders is pretty much everything. We get reality. It just highlights stuff that you just don't imagine sitting here in a building in Chicago. We've been focused on not just how the bikes are used, but how they're seen, what kind of modifications that they make. And then different riders have different relationships with their bikes as far as taking in the mechanics, maintaining them. There's a lot of labor involved with keeping all the communication flowing. For them, they're going to reach out immediately when they're having a problem because that bike is the livelihood. And so if they're having a problem, we get to them as soon as we can, regardless of where they are.
Days when I was using the ordinary bicycle, I was having a lot of breakdowns. And there were a lot of interference. Especially when the bicycle can get stuck in the mud. Whatever I get as a profit, 70% I used for repairing the bicycle. Because if you don't repair the bicycle, you will carry the bread on the sole and on the head. So when I use it as a buffer bicycle, I get totally 100% of my profit on a daily basis. My business, it really expanded. I'm agent of 4 companies, which I can supply perfect. And this is when they said that they don't plan for the future. You plan for your own future. You plan for the future of your family. Yes, it goes on. A bicycle is an ergonomic extension of the body. It just makes better use of your energy so you can cover more distance. One of the problems with that is by constraining the body to a certain type of movement, you're not able to compensate for different terrains. When you walk, you adjust your stride, you adjust your gait as a way to adapt to different terrains. You can't do that on a bicycle. And the way to overcome that is with multi-speed drivetrain. We've tested every type of drivetrain to try to put more than 1 year on a bike and survive. So what's the point of putting on 2 gears if after a month you only have 1 gear or no gears at all? A not working bike. I think we've finally come past something that's going to last for generations. It's World Bicycle Link's first patented technology. AK2 represents our best effort at durable multi-speed drivetrain suitable for our users' needs. What is very important in business is time.
This one, if you change the gears, it can go faster. Even if you're climbing the continent.
Instead of stopping somewhere and rest, you change the gears and continue in a soft gear. Yeah, so it's good for them that way. It's unique anywhere in the world. It's not a cheaper version of something else. It's something that's a result of us studying our users' needs and finding the best possible solution to produce that function in the bike. The question we ask with every choice is, how is this helping us get closer to our ideal? And all our design decisions go through that filter. We have many constraints on our product. Cost, of course, durability, harsh environments in which it's used, limited access to spare parts and maintenance, all of which make for a very challenging design environment. But that challenge is what makes it so exciting to work on. Without constraints, there's no need for creativity. Today, we are going to give out some mosquito nets to prevent malaria. To the most vulnerable households, the one displaced by the landslide. This place is very hard to reach. But if you reach here, you swim of purpose in this landslide. But tells the American passport the politician.
The Red Cross has 500,000 community health volunteers. They respond to any food shortage, they respond to any medical emergencies, and these people are all over the country. They have over 100 households to see, and when there is an emergency, it's even more than 100 households, and the timeline due to emergency is shorter. With how vast Uganda is, they cover distances of over 10, 15 kilometers. The Buffalo bicycle needs to be there. So it's just the right fit for Buffalo Bicycles and World Bicycle Relief to partner with the Red Cross. And we donated 1,250 bicycles.
I think we're beginning to demonstrate that rural transportation is really important, and bikes are a very effective way to do it. It's literally bringing an industrial revolution into an individual's life, and that was the big epiphany. We're impatient, so is most of our team. 1 million bikes would be an amazing accomplishment.
It's a different kind of urgency. The sooner you get these parts out, the sooner you're helping people. We all need to move from one point to the other. When I look back, I think I was called to do community work, but I didn't know how am I making everyone's life a better place to live? How is the world going to be a better place by me doing what I'm expected to do?
It's not a job to make a product successful. It's our job to make people who ride the bike successful. And I wake up and I can't do everything is successful. I learn every day. If you look at how it is in the organization, we are growing from somewhere to somewhere. And when people see growth, they want to grow with it. But I don't see it coming down. I see it going up. Is there anything else you want to talk about?
If I can.
East Africa is definitely much bigger than Zambia, Zimbabwe, but definitely Malawi. Is this on live? Malawi should be selling more bicycles than Kenya or Uganda. No shooting for Malawi. Aside from everything else, that's what I need. I need to beat Malawi. Anthony's a great guy. Yeah, but I mean, I'm gonna kick his ass. Dude, my English, beat him with the tape. Send it to me, so I slightly sent text to him. I don't know what happened.
That's all for us.
Yeah, and unless there's other questions, I think, when it comes to the product development side of things, we are, and this project in particular, the bike, I come from the bike industry, so I came from, and much of what the bike industry is focused on today is prototyping market, it's not focused on the market. There are ISO standards, there are things, there are testing programs, but they don't focus on where we are. That's why data acquisition, so that we can understand, develop some lab testing. Help us get at, right now, the way that we test is put stuff in the field, and that takes a long time to see what's gonna fit. Any other questions here?
The idea that you change bicycle.
Literally, it was a brainstorming with the advanced development group expand. We're trying to think of different projects. It's very difficult to get things robust enough, like the regular system where you're moving chain around, the dust and these things up. Internal like managers in your systems, those are really, really complicated. Once they have a problem, people can't maintain them. So what can we do? And so it's like, just put another chain on there and then just give them that finding here. It's so perfectly simple. Extremely easy to manufacture at especially once we get at to higher volumes. It's very, all the components inside are very ubiquitous, it's the same, varying ball size, they have on every keyboard out there, you open thing up and it's very obvious. Like, tried it, obviously, think about it, you've got two chains next to each other, your chain dimensions have to be close enough that you're not gonna have one chain derailing, so we didn't even know if we could get two ratios that made sense. We put in, just like anything else, prototyping, we put it on a bikes. And wow, this could work. We out in the field, people love it. So we down to develop it. I will say though, you'll also find that it's not a completely new idea. If you look at the history of bike, people have to put two chains on a bike, two chains on a bike. In the 1900s, like if you look back, everything's sort of been done before, but not in this particular way. So we did find that's where the good question. It's a very, if you have a strategy, I would go problems that are going to solving a particular problem is gonna affect those people. It's one of my problem, not every it's a lot of energy solving that. We are kind of looking at overall how to make it like better for biggest outlook. So we are very, very lucky in our model because we have these different countries that we operate in. And in these countries, the bikes are made in China, the components are made in China, and they're shipped to these countries. They're actually built, the bikes are built from scratch in the country. So we have these manufacturing facilities that have access to their communities. And then we have testing. So we do have, and then on top of that, we have bicycle shops in all of these. So we got an improvement that we want to evaluate for how effective it is or how well received it would be. And be very strategic about basing your let's focus our prototypes in that location and get the feedback from them. And then as we get more confident, very restricted on how much resource we have. So I would be very deliberate, very much it's all we to. Where are you going to set this?
I think we're running a little
Yeah.
bit behind schedule, so you want to station and then you guys.
Yeah, we do that, so there.
Okay, so I am Becca, the Gaia co-founder and technical lead, and I'm going to give a technical overview. And so this is designed for the competitors in the room to remind you everything about the problem statement so that it is fresh in your mind as you present. And then for the people who are new, to give you a sense of what is the problem that we as Gaia in partnership with WBR are actually solving for this competition. So yeah, I'll start with
some general technical background. Most of it will be the problem statement. And then I'll also give some sensor consideration technical background, particularly for those who may not be as familiar with electrical engineering, so that you can better understand the team's presentations to come. So GAIA has existed from its inception to try to fill the gap of a competitive project team that is actually doing good for the world in the form of addressing the United Nations Sustainable Development Goals. And so we set out to have in some way a competition that addressed these. And the form we arrived on is the current form of GAIA, where we're partnering with NGOs, non-governmental organizations, to solve specific problems in these different areas of the Sustainable Development Goals. And so our first partner, WindAid, that we worked with the last 2 years, they were solving affordable and clean energy by making wind turbines for rural electrification for people in rural areas of Trujillo and surrounding communities in Peru who do not have access to electricity. And then this year, now partnering with World Bicycle Relief, we have pivoted to addressing Sustainable Development Goals 1, 3, 4, and 5, and that's through like the 3 impact areas that WBR talked about in their presentation, the bikes being used for economic well-being, community health workers, and education, especially having a positive impact on girls' education. And so 78% is the proportion of the population of Africa that uses walking as their primary mode of transportation. And that's why the bicycle as a solution to rural mobility is like a really useful way to address the sustainable development goals, specifically on a larger scale. And that's something that GAIA is really excited about this year. Whereas last year we were helping a couple of families with the wind turbine, but now with the World Bicycle Relief Partnership and that like ecosystem that you guys described is being very built out and having a much larger ability to make impact. And so that brings us to the problem statement. What is actually a problem that needs solving, specifically that college students are able to address? And so when we had our initial conversations with Chris and the rest of the product development team at WBR, we talked about, in general, what are some potential things that you might want to redesign about the bikes in the future. And some of the ideas in the left column came about making the drivetrain more robust, having better knowledge and information to design the frame, fasteners, especially with regard to vibration, and then potentially rider comfort also in a vibration sort of way. And what we kept coming back to is in order to do these redesigns, it is imperative to have more data. And specifically, we figured out what data would be required to meaningfully inform these design decisions to make sure that the redesign would be so that the redesign is made with design requirements that correspond to the actual communities that WBR is serving, and not just to test standards that come, for example, from the International Standards Organization for regular road bicycles in the developed world, where the specification for force or vibration or anything would just be not relevant. And so that's how we landed on the problem statement being centered around build a sensor system to measure all these things to inform future potential redesigns. And so that brings us to the design requirements. And I'll summarize some key ones here. The biggest one just being the sensors, which quantities need to be measured, and laying out the types of considerations and values for each sensor that are relevant. And then lifetime, this sensor system is not supposed to be designed for, I guess, like main use. It's not like going to be a feature on every future Buffalo bicycle. This would specifically be tested by a few product specialists or in partnership with the testing team to collect that data in specific communities. And so the lifetime is about a year with testing locations in a couple different countries in Africa or Colombia, and then desiring 20 hours of operation time between charges if a rechargeable or like grid recharging system is used. And then supply chain, the requirement is not requiring the electronics to be sourced from within the program country. The electronics can be sourced from the United States. This is actually a big departure from last year's problem statement, where the whole idea for improving the wind turbine was locally sourced electronics, because that was a really big portion of their cost, was importing this charge controller from China, and there were lots of import tariffs and fees. And so that's what the Cornell team's last year design addressed, a locally sourced controller. But now this is not the focus of this year. Use, in some sense, whatever electronics you want. But the focus really is on the way that the sensors come together into a useful measurement system and how that can measure the loads and patterns of use in the particular program countries. And then there's also requirements on logging, the data format, and then there's a desire for a certain event button that someone riding the bicycle can press to indicate I observed something, to then look back in the data that something interesting happened there. And then usability is actually a really important requirement. Making sure that the sensors can be installed by the product specialists, so the mechanics who have limited electrical expertise but very deep like mechanical knowledge, and don't have access to all the same tools that we would in the United States, and making sure that the bicycle itself is still fully usable, particularly that rear carrier, as we saw in the video, people putting a lot of different really important like loads on the back of it, and so the sensor system should not interfere with that. And then the final requirement is a cost less than $500. And so the scoring is split into two categories. There's the design and documentation. This is more the engineering aspect of how is the system designed. Is it designed well from like an engineering design process sense? Does it meet all the core requirements? And then documentation, how well is that design communicated, especially in the constraints of being able to get that information across to the product specialists who may not be fluent in English and may not be well-versed in electronics, and making sure that it is still easy to assemble and use from their perspective. And then the larger portion of the score is the demonstration and test. And that, in my opinion, is the most exciting part. Does the system actually work? And so we will be assessing that later today. The actual ease of installation, how long does it take for Chris to put it together later today? Does it survive in the rain and the dust? And then does all the data that is desired actually get recorded? And so that is 8 points. And to give you a sense or a reminder of the timeline for this year's competition, we announced at the beginning of December, so right at the end of the fall semester, our partnership in the general topic of sensor systems for bicycles. And then in the end of February, released the problem statement with all the details and requirements. March 4th, we were able to release the CAD to teams. March 16th, adding some clarifications on those requirements, giving you the full information. And then today, the competition, which we've all been very excitedly awaiting. And what's up next? In June, we're going to have some community engagement trainings for the teams with our partnership with the Einhorn Center here at Cornell about best practices for working with communities, especially with communities who are very culturally different than your own. And that will inform the implementation trip in July. And then finally, a report about the results of that in August. And so then getting into some specifics about sensors, sort of a crash course in electrical engineering. So what is a sensing system? What does it consist of? There is some sort of physical process that needs to be sensed. And then the sensor is effectively a transducer that converts from typically the mechanical domain, but the domain of whatever the physical process is that you need to be sensing, to the electrical domain. And in this case, for the bike, that involves thinking about where mechanically is this sensor mounted and how is it attached? How are any, for example, loads or other information being transmitted to this sensor? And then in the electrical domain, the sensor will typically need to be powered. Some sensors are passive, and the sensor will, as a transducer does, output a signal that measures the quantity of interest. Then there is some wire connecting the sensor to the microcontroller, an area of sometimes important design interest because of the need to mitigate EMI. And then a microcontroller, a small computer that is querying the sensor values and then communicating with some sort of logger that logs the data to some sort of external storage medium for it to be retrieved. And so some terminology, analog versus digital. So an analog sensor is outputting a continuous value, usually a voltage, sometimes their current source analog, and that will usually get fed into an ADC, which is an analog to digital converter. That's what, for example, on an Arduino, the analog input pin, those are the pins that are equipped with ADCs, and the ADC converts that continuous amount of voltage to something that is discretized in the number of bits that the microcontroller is able to handle digitally. Whereas some sensors are already producing digital outputs themselves, and so they will typically have some sort of internal ADC and other, perhaps like a serial chip inside of them to produce their own digital waveforms. Some common ones are I2C and SPI, which will then interface with digital pins on a microcontroller. And the advantage of that is that it can be less prone to noise because it's already digitized as the signal is going from the wire between the sensor and the microcontroller. And so in the problem statement, we talked about these 6 sensor technical specs that teams were encouraged to think about for their sensor design. So the maximum and minimum data values, making sure that it's a reasonable range corresponding to what values would be physically expected in the different operating conditions. And then the bandwidth, referring to how frequently, it's related to how frequently the data is read and recorded. Precision has aspects related to both the discretization and the noise. Accuracy has aspects related to a static offset or a slow drift over time. and then filtering a type of signal processing, choosing the time constant for that, and then any type of data transformation and appropriately choosing the algorithm or formula for that. And so on the end of this presentation, I'm just going to go through each of these 6 in more detail. I'll skip the first one because that's pretty straightforward, but starting with bandwidth, and explain a little bit more about that so that you have more context when listening to the team's presentations. So for bandwidth, when you're thinking about a couple slides ago when I talked about the physical process that needs to be sensed, that process is occurring at some frequency that is relevant to what you're trying to measure. You may only care about the slow variations of that quantity over time, or you may need to resolve very quick high frequency changes in that quantity. And so that's basically what this means, is thinking about the frequency content of the process. And for example, is it 1 hertz? And that can set a requirement for your sensor selection. What bandwidth of sensor do I really need? And then the sensor itself will have a certain bandwidth. This transducer is able to accurately measure physical processes at this range of frequencies. Typically, it will be fine at low frequencies, but will have a maximum frequency. That's its bandwidth of the sensor itself. And so that is a really important quantity to select in the sensors. And another concept on the topic of bandwidth is transmission delay. And so transmission delay, basically, if you don't have a very high bandwidth, things are happening very slowly on your system. This is more of an issue when your sensors are being used to then control an actuator, and less so when you're just having sensors that you're logging. But say on a robot, the sensors then being used to control the robot to have it do whatever motion you're looking for. If there is insufficient bandwidth on the sensor side, you could have a transmission delay so both insufficient bandwidth on the sensor side or separately a transmission delay caused by something else if you have slow processing or a delay otherwise in the controller. And that can limit the bandwidth of the entire system. So then let's say if the robot is trying to touch something, it doesn't sense the fact that it has touched the thing yet because there's this delay, and then it will keep going. And so that can be an issue and is often what you'll see when talking about bandwidth. And I'm sort of drawing that distinction to also kind of point out that because we're not actuating anything, that aspect of bandwidth is less relevant here. And so those resources, while helpful to understand, are less the type of bandwidth that we're talking about here. And then other parts of the system that can potentially have their own bandwidth that might limit the overall bandwidth of the logging system, the digital communication protocol, or the ADC itself, are only rated to detect up to certain frequency of signal changes. There's a concept called the Nyquist frequency, which I won't get into the mathematics of, but if you are sampling at a certain rate in your microcontroller, it's possible to mistake what frequency you think the signal is when that sampling is too slow compared to the frequency content of the signal itself, and that's called the Nyquist frequency. And so that is another value that needs to be checked for the compatibility of the microcontroller sample rate and the sensor. And then finally, once the data is in the microcontroller, thinking about what frequency do I need to actually log this. Perhaps you want to measure with a higher frequency, but you don't need the data as often, and so then you might log, for example, only once a second, even if you're reading your data at 10 times a second, or a bandwidth of 10 hertz. And then the next concept is precision. This can occur with quantization and noise. Precision is when my log says that the sensor is reading a value of whatever number, 8, is it actually 8, or could it be 8.1? And so whenever you have an ADC, that introduces quantization, and it's best practice to use the full range of the ADC. And so if a microcontroller has an input pin range on its ADC of 0 to 3.3 volts, which is pretty typical, that will be mapped to, if it's a 16-bit ADC, to integer values between 0 and 2 to the 16th minus 1. Or for a different number of bits, it's 2 to that, whatever that number of bits is that the ADC is. And because you now have sort of like staircase these quantizations, you want to be using the full range of the ADC, because that means that your percent error in the quantization is lower of your signal. And then noise is any type of random variation on top of the desired signal. Typically noise is high frequency. We quantify this with a signal to noise ratio. You want that to be as high as possible. White noise means that there's an equal amount of noise at all frequency, but different noise processes will have different power spectral densities or distributions of how much fast versus slow noise there is. And it is relevant to think about in specifying a sensor system, what the bandwidth of those different noise processes are and where are they coming from. Noise could come from EMI, so that's electromagnetic interference. For example, in this room, there is an outlet over there, and that means that like we are all capacitors, and that is going at 120 volts, 60 hertz, and the electric charge is accumulating on any conductive surface, and that is a form of EMI that if you were to, for example, like hook up a voltmeter to me right now, depending on how sensitive it is, you could read the 60 hertz noise from the room, from just like the grid. And so that is a thing that you might especially see when you're working with power supplies, picking up that EMI. It's also an issue when you have magnetics. This was something we talked about last year with the wind turbines. The motors are like just spewing EMI, but there's also considerations for if you're using, for example, a magnet for a Hall effect sensor, that can also be producing EMI, which could be messing things up. Other sources of noise, poor installation of a sensor, low sensor quality, just the cheap ones will tend to have more noise. There's also the possibility of ripple in the input voltage. And so if you're powering your sensor with 5 volts, but your 5 volt is not actually a steady 5 volts, it's 5 volts being produced with a DC-DC converter or some other type of electronics that makes it kind of have this ripple over time. Depending on the sensor electronics, that ripple could make its way into the output signal, and that would need to be addressed so that you don't mistakenly see that. And then finally, perhaps there are just these small variations in the actual true signal. It's not like fake noise, it would be, I guess, real noise, but it still might be variations that are a higher frequency than you want. And that kind of goes back to the bandwidth question. Real signal content above some bandwidth is just noise. And then accuracy. So there may be differences in a sensor's accuracy that could be a static offset. Always over time, it's off by this amount. When you look at a sensor data sheet, you might see tolerances for this much absolute error, this much relative error. And these static offsets can be mitigated usually by calibration. And one common source of a static offset error would be in resistor tolerances used in a sensing setup. And so making sure to where necessary, use resistors of the appropriate precision to mitigate some of that static offset. And then finally, with slow drift, sensors can drift according to the environmental conditions. Temperature is a really big one. Also humidity, just like amount of charge in the atmosphere, other random things that can affect the sensor that may mean it needs recalibration over time. And then another possible source of a slow drift error is integrator accumulation. So if you are trying to get position by measuring velocity, which may be something that teams want to do for measuring the distance that the bike has been ridden, every time you integrate velocity, velocity will have some noise on it, and then you're summing up that noise that becomes the sum stays in your estimate of position, and so that integral accumulation error can lead to a slow drift error in accuracy, and so that would also need to be quantified for any sensor solutions that use integration. All right, and then getting near the end, filtering and signal processing. The most common one you'll see is low-pass filtering. That removes the high-frequency noise, similar to what we've been talking about with bandwidth, and teams are encouraged to choose the time constant wisely, sort of the same thing as choosing your bandwidth wisely, but if you're going to have a low-pass filter, make sure that you are not filtering out important high-frequency signal content, but also that you're filtering out all the stuff you don't want, because the low-pass filter only lets the lower frequency signal content stay there. This is in hardware commonly implemented with a capacitor, and in software can just be implemented with a moving average filter. So for example, so take an average over the last 10 samples and use that as your data point. That's a really easy software implementation of a low-pass filter. And also pointing out, you'll know this if you've taken like a signal processing class, but a low-pass filter introduces lag, and so that's another reason to choose the time constant wisely. If you, let's use the example of the software moving average implementation. If you are averaging over the last like 1,000 seconds, now you have such a really large lag that depending on like the frequency content, if your signal is meaningfully changing every 10 seconds, then that would be an unacceptable amount of lag. And then high pass filter, a different type of filter that can also be achieved with like standard linear components. But instead of a low pass, which removes the noise, a high pass filter removes the constant of a signal and it leaves only the variation. And so that is less commonly used, but still might find its use. If, for example, you know that with one of these you have an accuracy offset, whether it's static or slow drift, and you're trying to remove that, if you're trying to measure some frequency content like vibration, then a high pass filter may be useful. And again, you need to know the frequency band of interest. And other ways of signal processing, for example, amplification and buffering, are also things that you'll potentially hear about from the teams today, and I won't go into them as much, but there's many considerations on the electrical engineering side to make sure that the quality of your logged data is as high as possible. And then transformation. So one of the data quantities of interest is vibration, and vibration occurs at a certain frequency. And when you're measuring from a sensor, you're measuring at individual points in time, and to know how those points in time correspond to oscillations at different frequencies, a transformation such as the fast Fourier transform is needed to transform the data from the time to the frequency domain. And this is how, for example, it would be getting the ultimate data that could be fed into WBR's like vibration table to inform those vibration tests. But the thing to be careful of is that when you do that transformation, it is removing information. So you no longer have, for example, the peak amplitude in time, because that's not a feature of the frequency domain signal, or kurtosis, which is a type of like nonlinearity-ish in the signal. And so if those aspects are important, then you would need to log in the time domain and have frequency domain be in post-processing as opposed to logging in the frequency domain. And finally, transformation could be necessary for other dynamics. The most relevant one that we have talked to teams about is with the accelerometer. When an accelerometer is placed at a point on the bicycle that is not its center of rotation, then you will see fictitious forces, is what they're called in dynamics, that basically when a rotation is happening, even when there's no linear acceleration, a linear acceleration will be measured based on the lever arm from the center of rotation to the accelerometer. And so that can be accounted for and transformed out with some dynamics math. You just need to know where the center of rotation is. And so that will also probably come up later today. And so that's the end of the technical stuff, but are there any questions? Okay, thank you. So next up, we have the team presentations. Who's first? UCSD is first. Did you email, share?
So I can share right now.
Okay, yeah. If you want to send it to either the guide or to the colleges or to
Share.
Is it a Google Doc or is it an email?
No.
Okay, sure. Yeah. And actually, so since we're starting the competitor presentation, I'll point out. And so make sure that judges even get one. Okay. And then we also are encouraging anyone else to take a short sheet, even if you're not like one of the judges, just to follow along. And this will also be a great way for teams to see. So, that. So, you guys will have um, half an hour for the presentation, and just so that you can easily keep track of time, I have this timer up here, and so I'll set it for 30, and like you'll be able to visually see how much you have left. And it will beep at the end. And if you do end up going over and it beeps, just try to finish up within the next like minute or two.
All right, sounds great.
Thank you.
Thank you.
Yeah, that's the look guy.
All right. Hello, everyone. We are UCSD's GAIA team, and my name is Daniel Villaseñor.
My name is Thomas Jaws.
My name is Ari Wen.
I'm Alfredo Gonzalez.
Now, we have other members that we would like to acknowledge. And yes, this is our actual bike sensor that we have been working on for the past couple months. All right, so everything starts here with our microcontroller. Now, with our Arduino, we chose to use the Arduino and we wanted to make sure that it would stay in, or it would survive rough conditions, especially while being driven in the mud or driven in the rain. We chose to use a protective case that we could have enough space to add other sensors inside of, while also protecting our microcontroller. As for placement, we decided that we would like to place the actual microcontroller under the seat, in between the top bracket and between this tube right here. And that would ensure that all of our components are safe, especially during travel. And this would ensure that all of the actual data is kept in a safe location. Because while someone is driving, and if, for example, the placement is not in the best position, you might risk losing that data, especially when data is very beneficial in terms of working on being able to improve your sensor or bike. All right. So here are our sensors. All right.
So, for our bike specifically, we decided to incorporate something called a strain gauge. And a strain gauge essentially measures how much something has bent or flexed. And later I'll explain more of why we use the bikes of a strain gauge. But currently we place the strain gauges on the locations on the bike that we thought might flex the most. So like all these three major connection points are places where if a load is placed on the bike would bend a lot.
So as for power, we decided to use a rechargeable battery. Now, one of the main things that we wanted to do was, or one of the main things that we considered was that we didn't want the actual back load to be obstructed, especially when a driver is carrying cargo. It may get in the way. So as for our placement, we decided to place our battery near the or right under the seat, as a way to not have it in the way not have our battery in the way of other it's next to our Arduino, and it can easily be connected without having cables running through and possibly getting tangled up and destroyed while riding. Now for rechargeable, we chose a rechargeable battery as we thought that it would be great. Now, one of the main issues or actual concerns that we had was to use a battery that would last quite a while, especially while a driver is driving through, let's say, a mountain or an area where there's no power, in order to recharge the battery. So one of the main things that we actually wanted to do was ensure that the drivers can be able to drive long distances without having to worry about the loss of power and continue gathering that data, which, if not considered, it would render these sensors useless. All right. So here's our drivetrain torque sensor. Thomas, would you like to cover that?
Sure. So obviously one of the biggest considerations that we need to figure out was, especially due to the rough terrain, there is plenty of torque being put onto the pedals of the bike. And as such, we decided to incorporate something called a torque sensor, which is a quite expensive component that essentially measures how much power is driven through the wheels. This allows us to calculate multiple things, like for instance, obviously how much torque. It also can allow us to tell the angle of the bicycle, because when you're going uphill, you'll be using more torque. And it also allows us to figure out exactly which gear you're in, because if you're in a lower gear, you use less torque.
Now, one of the main things that we decided to do was have our torque sensor. We would like to place our torque sensor near the bottom bracket, which would actually be around here. One of the main things that we saw in the Buffalo bicycle was that it has a removable kind of area near the gear and the pedal, where you would be able to take out the existing components and then swap that for the drivetrain torque sensor right there. And now this would be an easier replacement, where the only issue that we encountered was having the wires in a awkward location. Now, to be able to kind of work around this, we decided either using a remote or a way to transfer our data remotely, or being able to kind of drill a hole through the bottom section right here, if possible. This would ensure that this would ensure that our cables are not interfering with any of the with the actual bike, in order to ensure that the rider has a comfortable experience while riding their bike. So now our next sensor will be the acceleration/vibration sensor. And we decided to place this near the center of mass, which we determined was actually near the middle of the tube under the saddle. Now, the accelerometer would basically be connected near our Arduino, and we would make sure that we're able to mount this in a specific way that we will cover in a bit. Now, Thomas, would you?
As for the specific sensor itself, we decided to go for a triple axis accelerometer that they can also figure out what direction the bicycle itself is accelerating, and also we can calculate side to side motion, which with the rough terrain we kind of need, because I feel like most bicyclists would go side to side a lot. And as such, that's why you decided to go for the specific accelerometer.
Yes. Okay, so our cadence sensor. As for the cadence sensor, we consider different things, such as a Hall effect sensor, or maybe a sensor that was already produced. Now, one of the main problems that we had was how could we determine the actual rotations through our crank arm, which is actually right here. And we wanted to make sure that we would have a kind of secure way of counting our or tracking our cadence. And we decided to use something which is a Hall effect sensor, where a magnet can be attached in order to count the RPM of our bicycle. And then this would also prevent cables from being attached through, like, from the pedal, and it would ensure that our riders aren't kind of tearing those wires up as they drive, especially when these kind of especially since pedaling is one of the most important parts of riding a bicycle. Now, this actually related to one of the requirements for the competition, where we had to track the rotations of on the shaft of the bicycle, and we determined that this form of using cadence sensor would be the best.
Oh, one more thing I wanted to add right before. While we decided to use a Hall effect sensor at the very end, we originally considered using a pre-manufactured cadence sensor. However, the slight issue is that most modern cadence sensors are wireless due to the fact that, wired cadence sensors kind of wrap around each other as you're pedaling. However, we couldn't exactly use a wireless cadence sensor because our board that we decided to use, the Arduino, can only support Wi-Fi but not Bluetooth. Another consideration was the programming aspect of this. We decided would be pretty difficult to measure, a Bluetooth cadence sensor because you had to figure out Bluetooth ports and all of that. And as such, we just decided to go with the Hall effect sensor.
Yes. And although both can be done, we decided that this would be one of the best options. All right. Alfredo, would you like to talk about the weight sensors?
I'll just talk about like the wire.
Go ahead.
Do you guys know more about this?
All right. So, So as for strain gauges, something that we covered earlier, we would like to be able to measure the stress on the areas that are most likely going to receive the most or flex the most. And this is very important when an individual would like to measure the actual maximum capacity that a bicycle can handle. And this could be used to improve the actual bicycle as in terms of being able to learn how to gather data for being able to just determine next steps in planning. And we decided that some of the places we were going to place some of these weight sensors or these strain gauges were near the saddle and under the back fork. Another location that we were deciding on adding the actual strain gauges was right here near the front fork, where we determined that as a rider is maybe shifting over to hold the actual handlebars, they might be putting weight down, especially from the front, which would in turn kind of put a lot of like strain on the front fork and could change how like the actual riders are or how the bike will react to that. Now, these were some of the things that we went over, and we determined that these would be some of the best locations for our strain gauges.
Also, another thing that I want to mention is how like interconnected all these parts are. For instance, we figured out that when there's a weight near the back and when there's a rider near the middle of the bike, that means the rider might lean a bit more to the front when the bicycle is going up the hill. Hence why we added a torque sensor and a weight sensor. That way we can calculate all of these values to figure out how much force. Because since we had the torque sensor already implemented, if there is more weight in the back, the rider would put more torque in the front. That was our calculation, and as such, we decided to add weight sensors so that we could figure out just exactly how much torque is needed, and then what factors affect the amount of torque that the rider's pushing.
All right, so GPS. One of the main things that we noticed for the requirements was that we had to determine location of the bicycle. And we determined that we would like to use a GPS sensor that would be connected to our Arduino, which, as we showed, we would have the actual casing protecting the GPS, especially since it's something very small that we could fit onto or into that casing. We determined that this was probably the best location to place our GPS. And it would not take up much room. And one of the main reasons we decided to place our sensor or our GPS here was that if we were to place the actual kind of sensor near the handlebar or any other location, we would have different cables running through, and this could be a bit uncomfortable for the rider. Now, with the actual tracking, we decided that since we can't use Wi-Fi, it's a bit tough to kind of place this sensor anywhere else. So in terms of being able to track effectively, we decided that we would like to place this in the actual casing in order for it to be safe and secure.
As aforementioned, this is the drivetrain torque sensors that we were talking about. So I think we've already been over this. So
Yes, but one of the main things that we wanted to mention here in this slide was that this is how the actual bottom bracket looks. Now, when you are able to remove this specific part, you're able to kind of fit that sensor inside. And we determined that we could either place the torque sensor inside or under, depending on where the actual the best kind of location is to place the sensor. If maybe the sensor that you purchased does not fit inside of the area, you'd be able to kind of work against that. Now, we were also thinking about measuring, or we would like to determine measuring the force applied on the pedals while taking our cadence into like consideration. So, all right. Harry, would you like to cover this? Okay. All right. So the real-time clock. One of the things that we noticed on the requirements for this competition was that we had to incorporate and use a real-time clock. This could be useful when maybe being paired up with the GPS, as you'd be able to determine location and where the individual riding the bicycle will be in order to determine maybe if there was rain that day, or if they were traveling through a location with unstable terrain. This would be important to be able to understand maybe what time, and it would be useful when tracking what and where these individuals are riding in order to understand the conditions that they're riding in. Now, we determined that the clock was also a very small, or this sensor would be very small, and we could actually put this inside of our casing along with our microcontroller. And we believed that it would be best for us to place this clock inside of that casing because it would keep it safe, along with not obstructing any other parts of the bicycle. So that was what we determined. And yes, so the next sensor that we will cover is the string gauge, which we have actually covered. And we would like to
wait, can I mention some stuff?
Yes.
So actually, during this process, we were able to somehow collaborate with the Cornell team, and they actually let us know that there's a way. So originally, what we were planning on doing was we decided to just stick a strain gauge on each side of these. However, there's a few issues with that. First of all, we couldn't figure out how much error a strain gauge has because when a mass is put on a bike, chassis will obviously flex a bit, but we didn't know how much it would flex comparatively to like the strain gauges, especially because if you have a really sensitive strain gauge, then it would measure it a lot better than a not so sensitive strain gauge. And then there's also issues of error because one single strain gauge cannot be enough to measure something accurately. And as such, we were with some collaboration and help with the Cornell team, we figured out that there's something called a Wheatstone circuit, where it's around 4 strain gauges combined, and that would reduce the amount of error into our chassis. However, as we talked with the Cornell team, there was a slight issue with the Wheatstone circuit, and it was a bit big. So we were thinking of originally buying smaller, strain gauges, or even going for a half circuit. So instead of a full Wheatstone circuit that is around 4 strain gauges, you'd only go for 2 strain gauges. which would actually increase the amount of air compared to a full Wheatstone circuit, but would take less space. So that was our final consideration when we were thinking of implementing these sensors.
Oh, actually, one more thing that I would like to mention. We were looking at this company named HBK, and they make custom e-bike sensors. We were planning on, or one of the main things that they used were foil type string gauges, which were very different from, or they were pretty similar, but a little bit different. Now, this would kind of help us understand, and they would be a different option when considering your torque sensors. They might be a bit expensive though. So judging on the actual price, this could be an option. All right, display.
Um, so after gathering all the data from the sensor, we plan to use e-ink to display what we've collected. And we chose this option because it has the lowest power consumption out of all, and it can display vital data we've collected through the sensors. And so do you want to cover the
Oh, sure. So the board that we were using, the Arduino R4 specifically, used a 5-volt input as the power supply. And as such, we look specifically for a 5-volt battery that is decently large and has a decent amount of capacity while also being waterproof. And we found a few options. This is just one of the ones that were listed, but we specifically look for lithium ion battery because of pure efficiency. As a person who worked at RC cars, I was thinking originally of using a LiPo, lithium polymer battery, but that wasn't as efficient as a full-fledged lithium ion battery. So as such, this was our battery consideration.
So there are many vital parts in our design, but there are also sensors and parts that we've decided to get rid of in order to maximize the efficiency of the cost we put into the design. And load cells is one of the parts that we consider to take off. Initially, the reason why we're considering it is because it is an ideal housing for the strain gauge. It um, it measures the flex very accurately, so we'd like to have a place in our design to host it. But the reason why we didn't implement it is that the cost effectiveness is not really worth it. And also it is limited to linear motion, and in reality, it is different. It is different to implement.
Actually, on the price, it's kind of funny because a packet of strain gauges, like a set of 8 on Amazon, is like $7 or $10, but a singular a load cell, it's like $30-$40. And we were like, that is not worth the price. I mean, while it is way more secure and way more durable than a strain gauge, we were thinking of originally coating the strain gauges with some sort of epoxy. That way they would stay more coated and more protected from the environment. And that would be way more cost effective than buying a $30 load cell.
Yes. And the second thing we decided to take off is the brake pad. And initially, we're using the Hall effect sensor to measure braking. And we will be able to calculate using numerical data to see how much the pads are being worn out. But the reason why we didn't implement it is obviously to reduce the cost, because wear can be visually observed, and we can implement some directions into locating where the wears are and how to repair on time, and it would be more cost effective than installing a brake pad.
So, for our CAD models, some of the things that we were thinking of using were custom P clamps, which could be adjusted based on your specific needs. So, while we created these P clamps, we decided that we would like to 3D print them. Now, in terms of, or when thinking about 3D printing, we considered at first PLA. However, one of the things in personal experience, I well, PLA isn't the best for these extreme weather conditions. Now, when placing these or when placing this in different like conditions such as humidity, high humidity, you'll notice that the since the PLA is made of around corn syrup, I think, or
It's a biomaterial.
yes, it is, and it will tend to absorb and deform, and it'll break. So instead of using PLA, we decided to use PETG or ABS, which one ABS is very tough compared to PLA. It's used in many other plastics. However, it's a bit harder to print since you need a specific type of printer that will ensure like or that will have a casing and while actually printing it might emit like toxic fumes. PETG is a bit easier to work with, and it will still ensure that the or the material will stay intact when in these extreme weather conditions. So we decided to create 3 different models where we created a torque sensor mount, an accelerometer mount, and a breadboard mount. Now, the breadboard mount could help us install the actual casing where our breadboard would or our microcontroller would be in. And as for the accelerometer, we wanted to make sure that it would stay in place, especially since we were thinking about putting it under the actual saddle. We wanted to make sure that it would stay in that specific location. Along with the torque sensor, this could help us if our actual torque sensor is not it doesn't fit in the desired location. So these were some of the CAD models that we considered. And yeah. All right. So here are wire connection ideas that we have.
Yeah, okay. So obviously connecting our wires is one of the most difficult things, especially with the fact that they can get tangled up and it brings everything together. So the 2 things we wanted to use were Dean's and XT60. So the great thing about Dean's, like for example, is that so we took into account the fact that one of the scoring guidelines, one of the big parts of this was um putting together the bike sensor with ease. And so the great thing with the Deans is that basically once you just do a little bit of soldering and you have an idea of where you want everything to be, these can be moved around super easily. And so that's why we had chose these, taking into the scoring guideline into account.
And what? Okay.
So another thing about the wire connection thing is that while it is another idea that we are thinking outside of Dean's was something called XT60, which is another type of connector that's way more like secure and way more dust resistant because it has this housing onto the female end of the connector. However, the slight issues from personal experience, I use XC90s for my RC car, and those tend to break often, especially this specific section. And that's why we were originally thinking of using this first, but then we realized after multiple tries and stuff that this section would probably break off, and then the connector would not be working as properly. So, and essentially we decided to connect everything using Dean's cables.
Yes, and it will just make sure that our mechanics aren't if they don't have the soldering materials. This takes that into consideration and makes everything a lot simpler. All right, so our price, these were some of the, this was the price for our materials, which would come around $248 with shipping and tax. And yeah, so.
We also prioritize getting the supplies from domestic suppliers so that we can get increase and accessibility and stability. Yeah.
Yeah. All right. Now we wanted to thank you. Thank you to Cornell University. Thank you to AJ and Becca for helping us out a lot during this process. Thank you for the Gaia organizers, and finally the World Bicycle Relief. Yeah, we look forward. Yeah.
Any questions?
Finish just in time. Yeah, we can do a couple of questions if you guys want to walk like over to that side and do questions, and then meanwhile I'll get Cornell team set up.
Scale wise, what is the size?
The mic controller is like this. It's actually bigger more than I originally had to say.
So, sorry, it's like trying to, like, you play around with the.
Slight issue that before we could order the parts, sadly, one of the data failure and couldn't see. We couldn't order the parts. We couldn't order the parts. Yeah. However, but we were able to put our other the sorry. So we had other microcontrollers. We had a Raspberry Pi, ESP32 that was running around. And we were just figuring out, how to fire those up. So, and we figured out that the Arduino is kind of an extension of that. Now, the actual Arduino core that we chose, it was around 22 to 30 or 22 by 30 millimeters. So it's not too large, but it does take photos. Now the actual casing can be adjusted which size we want. We found a specific kind of manufacturer that has different sizes, and we believe that she appreciates. And if so, you're able to kind of tailor that to you. And we believe that was very important.
And then it was the microcontroller, battery, that was all thinking would fit.
Yeah, and the battery itself would be outside. Right. Because it had a through. Yeah.
You're watching.
Yeah, I mean, I guess, the. Definitely on the mechanical side of things, which, and you also mentioned, you mentioned a crank mounted or some sort of compared to bottom bracket, but you didn't really talk about why you chose the bottom bracket side.
Yes, so when we so we briefly choices considered, and the way that we understood it was that we would hold actual mechanism that I first chips on heavy. We is that that use the instruction specification, and we consider using on
You don't.
if that actually
You're gonna still.
it would be a bit better than here. That's like the optimal choice. Because to ensure that everything is in place. Better repeating of that. So, also because of how that happens. I think however, while we release these features for them, just think inside stuff. I think there's one specific. So as such, we're thinking just in case you might be, also pretty a small out within that side. Yes. And if not, if like that possibility. So
That camera is so long. Can I just take it onto it? Can you take that camera?
also use
Yeah.
was not idea of this group, but then you realize it is a wired all that sense effect. It requires you to make a table of plan. Sorry, we can kind of screwed up. Thank you very much.
Yeah.
Yeah.
I mean, something you guys got through like a concept work that you were able to consider players. Yeah, it was about the football. Oh, yeah, it definitely is extremely challenging time. So it's
Like, how does this timer work?
Yes, so we'll set it for 30 and you
Is it
like
gonna go automatically like back?
yeah, it's
Already
automatically
started.
counting.
Okay.
And so this is the color is how much you have
Okay.
left.
Perfect.
And the beeper is on.
Okay. I'll place it.
But I'm gonna set it to like 31 because I'm gonna move myself over there. So that's yeah, I better.
Okay. No, sounds good. Huh? Yeah, you can just leave it there. Yeah. You guys need that timer. Yeah.
May begin. Thank you.
Hi, we're the members from engineering competitor for sustainability. I'm the current president, Iris, and here's our members.
I'm Jenna. I'm Annalisa.
I'm Nico Ross. We have two.
For this year, we are glad to focus on this bike problem, and I just want to take a second, so everybody is on the same page. And the problem statement is we want to optimize the withstand diverse terrain, weather condition, local capacity, and users' practice needs. And also, since it's our mission, we're gonna keep this part short. The project goal we are focused on is to create a working prototype in Ithaca because we're basically locally based here. And also during the June, hopefully we can get our prototype work with iHorse centers. So get it have a run before it get onto the trip. And we are focusing on design a sensor suit which collects data on drivetrain torque, frame load, and terrain-induced vibration. These are the three mainly focus we target on in this problem statement. Although we know we are expected to do more, but we try to optimize our result based on the realistic reasons like time, locations. And also we try to incorporate the design of the casing and housing for the sensor systems to make sure the durability of the whole sensor system is good for a long-term experiment locally. And we also want our design to be not interference with the user experience. People won't get bothered when riding a bike because existence of our sensing system. So we definitely took a lot of efforts on where the placement of the sensor would be. And yeah, we collect the data. And yeah, we're probably also gonna do a lot of future redesign just to optimize the data analysis and also handling the noise well. And the second goal is we want to also keep it simple because it's gonna be instruction manual for the people who are not familiar with the design not much. So we want to simplify the process to make an assembly is a really simple thing which can basically be achieved by any members in the community. This is overview I just bring up. and we will go into details of like each column. And for our methodology this semester generally is like we will try to work on like each system individually, but you know, like it's like a whole system, so it's gonna be a lot of like overlap. So we definitely take a lot of like forward and backward, a middle work between them, shift around. So and we also spend a lot of time on like sensor collection. We are gonna see a lot of justification on which sensor we pick and what kind of other choices we use to think about and why they're not working. And the bonding strategy is crazy. Like we actually spend like a couple of nights like to just play with the bike randomly in the hallway and see is like the bonding strategies actually work. It won't like just like get off the bike when the wheel starts to speed. And yeah, for like we definitely hopefully we have time to focus on the 5 and 6 more and to get the sensor have more reasonable data and also validate the system.
Yeah, so this is just like a schematic of the overall placement of our sensors. So we would have the Hall effect sensor right near the drivetrain, like on the little bar, and then the two magnets on opposite sides of the wheel. And then and then you want to have the Hall effect sensor be close enough to where the magnets are so that when they pass by, it can detect the change in field.
It's denoted in the graph as like all those green marks.
Yeah. And then the red, we have the accelerometer, and then that's also where we would have the Arduino, where all the sensors would connect to for the data collection. And then the strain gauges we decided to place in 3 different locations, ideally. So we weren't able to fully get them up and on the bike, but these were the places that we decided they would best be located.
Yeah, after being so forced. It's a pretty standard like frame for the actual shape, so it's very the best.
Let's go the physical bike here. Just mapping whatever's on the board. The 2 magnets are here. That nice purple pink, very nice cool casing is the Hall effect one, and it's here. And then our main Arduino port is there.
To the zoom in of like how the Hall effect sensor casing, and this is the casing for the Arduino board and also accelerometer.
So for the Hall effect sensor, we installed that on the drivetrain. So it would, each time the magnets pass by the sensor, it would detect the change in the magnetic field. So then you could calculate how frequently they're passing by and then compute how much the wheel is spinning and then convert that into the linear speed.
We'll talk more about why we did Hall effect sensor. We've had actually very similar considerations to the CSD team. Hall effect sensors are cheap, they're really light, and they work quite well actually. But the problem is they have to be really close to the magnet. So it makes it a little bit difficult to properly mount it right there. So we're still working on getting the proper mounting in that exact place, but it works well for measuring speed.
Also, the reason we like give up on the accelerometer is first is like accelerometer is, you know, is can measure like the linear and angular acceleration. First is like which means like we cannot directly get the linear speed out of it. We need to do like some integration. And also if you use like accelerometer, it means like we need to basically have it at the, I guess, like the center of the mass and take consider of the center of mass and the center of rotation to counteract some of the effects. So that's why we go straight to the Hall effect sensor. Yeah.
Yeah, so the signal is digital, it's not analog. And so it's not a simple like it's on or it's off. So you had to decide on a tolerance for when the magnet has passed by. And this can be an issue if there's other magnets around. And so that becomes a problem when we have like all these different sensors around in the same place. Fortunately, these magnets are pretty strong. And so even at a fast speed, we were able to get it to be very consistent. And so it only detects the magnets. And then again, that runs into the problem of colliding with the brakes. This is just the wiring diagram that we use to help figure out the power and stuff.
I guess like it's like so almost figure out like feel like we just figure it out better than like measure the vibrations steps. It's like after the minutes, and we'll still have to do more like data signal processing to figure out like baseline like accelerations we get like little vibrations, but yeah, we kind of repurpose the
Yeah, we use 50/50. The interface is really easy with our Arduino. And it gives you pitch, roll, and XYZ linear action. So it gives you a lot of data. Really helpful.
And later we'll talk about
Here's come to like the string gauges. String gauge is, as USSD team also mentioned, we use this string gauge instead to measure like the loads along the frames. And first we incorporate the Wheelstone bridges because this one can better reflect the change of the stress and strain along the frame. So we have the diagram of the Wheelstone bridge here. And it's basically the mechanism is like it changes the measured velocity by changes happening in the resistance. So when we have the string gauges, let's say that it's like the current orientation is like this way. So we will want this thing like linearly along the frame to measure like the bending force along the load. So and it can happening, when a frame is like under the compression and tension. So ideally we can get like the stress along the frame. And yeah, we set up like the resistance to be the same as strain gauges. And yeah, I can address second.
So I guess a little more like the specs of the string gauge, which is you have a string gauge, so it has a resistance, but it's not like compressed or stretched. And they're kind of like what's up like gauge factors, the limits of how much resistance change you can have. You can experience maximum compression, tension you can experience before it breaks. So it has kind of built-in peak compensation. So like if there's like definitely change, so much time will adjust for that. So that'll be helpful for precision. We looked up this. We use the strain relationship to resistance change formula, and so based on the change in resistances we get, we can divide that by the 350 ohms and also by the gauge factor value to figure out the strain. And then maximum resistance is roughly increase some ohms, although realistically, since the strain is so small, we'll be likely getting much smaller units, which is what we found in telescope. There was a lot of issue with strain gauges. We also decided to simulate a little bit on Altispecs because we love Altispecs. So basically, we first obviously with like when all the resistances are 350 ohms, the V2 and V3 are like the voltage against the two ends would be 0 volts. But if you vary that a little bit, let's say, for example, the strain gauge compresses and then the ohm value increases to like 0.25 ohms. We notice the voltage will also increase by 5 millivolts. So it's very small. I think within like kind of 0 to 1 ohms, the increase in voltage or like the change in voltage is kind of linearly related to the change in resistance. We'll probably have siblings more intensely with about and these feel or accurate or it will fall, it will like become like drop off at higher resistance changes. But this will help us convert to calculate straight. And that was mentioned earlier about like the small signal to noise ratio, which is really bad because that's what we found in testing. Like, is my little change in distance that I want due to like the noise or because of like the shrinkage method progressing? And so then we found something that we used that we thought could help or increase the signal to noise ratio is so we decided to use an op-amp because it could take the different voltage outputs from the Wheatstone bridge and then kind of just boost it up. So by choosing our resistor value, the feedback resistor and input resistor value ratios carefully, we can set the gain. We'll probably have to do like at least 1,000 to get at least a volt, which will help our like maximize the range of the argument because the argument can take so that maps to anywhere from 0 to I think 1,024 bits. I think it's like 10-bit resolution by default. So that maps to that many bits. And so based on that, once we read the data from the Arduino, using the Arduino from the op-amp, we can kind of reverse calculate and get our
I also think like during our debugging process from a mechanical point, the string gauges happen to have like pretty thin wire. So we have a lot of problems just like by integrate it into like our circuit or simplify or minimize the circuit used for string gauges because we know like we want to use string gauges along the frame, which is like actually less likely to provide us with like flight plane where we can just like stick our casing for like the autonomy like accelerometer or like high field sensor on. So that's definitely something we're gonna put efforts more on. Yeah. Yeah.
But the offer
Yeah, this is as we talked about before. Like we have like ideally we would have like the string gauges located right under the seat and at the forklift. And Jenna, do you want to talk more?
Yeah, so for the setup, like we showed the diagram before, but you would have 2 strain gauges for each of the Wheatstone bridge configurations, and then you would have one placed on a part of the bike where you'd expect it to experience strain, and then the other one where it wouldn't react to strain, so that it can account for temperature changes. So if the temperature changes, it'll affect both of the strain gauges, and then there will be overall no change in reading. But if there is actual strain, it will only affect one, so there will be the change in reading and they won't cancel out just from the temperature.
Yeah, this is what we brought up before basically. We definitely will look in the future to get some precision resistance, which is like likely have like the smallest tolerance. So like in that case, we don't want a tolerance of the resistance to interference with our measured change in stress on string gauges. Oh, sorry.
something else that we're considering all the circuit on a printed circuit board or PCB. And I'll basically take all, because like that was honestly our wiring. It looks great, but it's a scene that's like every time you shake it, the wires would jump. It's just, like you're able to troubleshoot, just because there's so much. And so just having all.
Yeah, and given that we're gonna try to move to PCB, these are a little bit temporary because we have red work holders and such. But essentially it just gives an idea of how we're trying to keep all the components safe from the dirt and everything. One of the major challenges is having wiring that moves between sensors, but it also will also go into the Arduino case without letting dirt into the case. So our solution right now is to have these blocks. They're printed with PLA, which is just temporary. That's what we had at the moment, but we'd like to move to ABS or wherever we can find that's stronger. To let the wires run through the boxes without getting dirt inside, we currently have this slot with a lip. It has a slot on the underside, so the wires can run under and then into the box, and that allows it to avoid having like an open area where anything can get in. And this is just the Arduino that we're using for reference, like in terms of size. It's taller than the Arduino because we have a GPS shield which interfaces directly with the Arduino, which allows you to do real-time clock and GPS calculations all in one. It's a really nice module that saves us a lot of work. Yeah.
This is a little bit on our like the process that we use. So first we initialize some variables that we checked if we wanted to like not constantly reading. Sometimes especially the accelerator can get overloaded and then stop reading. So that was kind of tricky for that. And then we have this things with data. I don't know if you want to talk about this. I'll talk about this. Okay. So then yeah, we just whatever data processing did, so conversion values to make the data readable, and then finally puts it down.
Yeah, so as mentioned, we're using an SD card right now. We got feedback that actually USB would be good for the that you guys are servicing. So I think that's a step that we want to take. SD was just easy for us at this point. And then we just write to the SD card with the USB format. The problem with the timer that's on the Arduino that it comes with is it doesn't have real-time information. So if it resets, it'll reset the time that it starts at. So it'll be offset by however long so the reset. And then the other issue that we were running into was our battery for some reason was not properly able to power it. We were using a 3.7 volt one, just supposed to work properly, but the just didn't have enough voltage, so we had to solder on the right connector to this battery that had the wrong connector on it, but we got that working. And then here's more about what is actually put onto the SD card. So we get the time. This is in milliseconds right now. Once we have the real-time clock module, it's easy. We have the code written for that. And then the output X, Y, and Z linear acceleration. These are what the waveforms look like before adding a filter. We have added a low-pass filter. We added a very conservative time constant because we haven't done enough testing on the bike in the terrain that it'll be used in, so we're not sure exactly what values we want to filter out for. So currently we're just removing like the really, really high-end stuff, but that's something that can be adjusted once we know more. And then here is the Hall effect readings. So every time the magnet passes by the Hall effect sensor, it'll trigger, and then once both of them go past, we know that a rotation has gone by. And of course, we have the circumference of the wheel. And so with both the time and the rotation and the circumference, we just calculate the speed.
Yeah, so here's our costs. This is for the the current model, which is we presented on the bike. The most expensive part was the Arduino. And then we approximated how much filament we used to 3D print the casings. So we had a total of like about $52, which is very nice and cheap. And then for our ideal case, which would be including the strain gauges and all the wiring and breadboards for the Wheatstone ridges, that brings our total like a little bit higher because the strain gauges also needs to be needs a specific glue to ensure to secure it onto the bike. That brings our total to $82, which is still a good cost. And then for our next steps, we would have to conduct further field testing to test our bikes to see if our system is like providing quality data and to see where we can improve on. And then we can also, through these testings, provide further optimizations for the system, improve wiring, which we got some tips for from the USC team. And then we can also have some validation for the assembly process. How can we improve on our instructions, how we communicate on the assembly, and how we can simplify it, our design as well. And so other areas where we can expand and improve, which is for data processing, how to interpret the accelerometer and strain gauge data, which we hadn't had the time yet to further develop. And then we could also refine documentations, and also add diagrams to help break the communication, the language barrier.
Currently, we're using tape. I think we're going to work towards getting an easier solution so that it can be easily like screwed on or whatever without the need for external materials that need to be reused each time. Yes.
Yeah, thank you. Well, any questions?
Actually, just a quick question because maybe I just don't know much about what type of manufacturing process, but you mentioned obviously using a breadboard and the issues with wires moving around on a breadboard. Like going to PCB. Is there
There's actually awesome 3D printers for PCBs, which I'm really excited about. They have these little copper boards and they essentially cut out all the parts that you don't need. And so only the copper remains, and that will like keep the wires into the right places. They're really cool.
Yeah, and that's relatively cool.
They have them at Cornell.
Like they fit in that $500 price.
They have them at Cornell that quite.
And you just chose a random, like a low your time constant as well as it's you were being conservative or how did you choose that and how would you adjust? I don't know how you would adjust it.
So when we're testing it, we can see like the high end. Now, it's pretty arbitrary to be really honest, but if we are able to ride this bike like a bunch, we can see we can like run it over rough patches so that it'll be spiking like high frequencies. And then we'll know that those are real, those are related to actually going on the ground place, and we can try to find like the maximum of minimum values. I think that's what we're gonna go about it. I'd honestly love to hear from somebody who's an expert about that. Particularly not knowledgeable about how to find like the perfect time constant.
What about electronics?
What about the drivetrain torque sensor again?
We don't have torque sensor. We don't have torque sensor.
Okay, that's what maybe you got confused. I maybe misheard you at the beginning. So you're doing acceleration, drivetrain rotation, not drivetrain torque.
Yeah.
Yes, we had issues with the physically how, because we bought all the materials to use strain gauges to measure torque for the drivetrain, but we had issues with the wiring. So there was no possible way we could incorporate that and like without the wiring getting tangled. So we just decided on to just calculate the speed with the Hall effect sensor.
Yeah, hopefully we are gonna get the speed like processed, and then we can get to know easily like the torque apply on the pedal and further like the worn out of the drivetrain.
There was other sensors that we were thinking of incorporating, but the delivery date for the arrival was after today, so it wasn't going to be feasible.
Really big, expensive, and they don't interface perfectly well. Yeah, I remember using. So I was going to use it. Thought it'd be a really nice solution because if you measure the torque that you're actually pushing and the actual outcome of how fast the wheel is spinning, you can use that to estimate corrosion and wear, which I thought would be really nice, but unfortunately, it's difficult to work accurately.
AJ, what's your question?
Yeah, next one is there this was
I would say like not like the easiest, but like we really glad like the Hall effect sensor works out, and fortunately we find out it's like digital and we are not stuck on an analog data like anymore. And the hardest, it's probably not the hardest, but like we are really spent on quite amount of time on the strain gauges because the mechanism is really like straightforward for me, but like I just don't know why we band-aid I think in a very reasonable way, like linearly along the strain gauges. And we had the Wellstone Bridge. Yeah, it's kind of frustrating, like it's not like giving us what we want.
We can keep going with questions.
Yeah. Oh, also for the strain gauges, it was kind of hard to ensure that everything was connected because the wires were so small and we were trying to solder them, but then that kind of was difficult to do without possibly like frying them. So yeah, there was just a lot of sources of error that it was hard to tell if our data was like reasonable.
Yeah, we had the whole system built, but we didn't want to like incorporate it into our bike system right now because we weren't sure if like this data was accurate. So we wanted to like we were confident in our accelerometer and Hall effect sensor, and not so much with the data we were receiving from the strain gauges. So we decided not to include them just because we weren't completely sure that the data we were reading was from the strain gauges or just noise.
Yeah, Buka.
Could you mention, does your system include a dead button or indicator?
Like it's just there's also the reset button. Yeah. So reset button, there's a reset button on it, but there isn't an enter that button. Like there's a button to start logging and stuff, but there isn't a button to say like something.
Any question from UCSD team?
Spot.
Yeah. Oh, I think it's just one kind of like glue specifically adhesive for like the string gauge material. But since like we didn't have it working in the lab, so like we were just trying to manually like simulate like the stress or like the forces along the frame. So we didn't eventually put it up there on a frame, like actually using that adhesive glue we are talking about, because we just don't want to. Also, like, yeah, we don't actually have like plenty of the string gauges, so we kind of don't want to waste like any of them. So we just like not like put the string gauge onto the bike yet. Yeah, that glue is like is we found the glue like you're not find a glue like commonly used for string gauges. I think it's just like that adhesive is like pretty good with the material.
It's like a
Yeah. And then there's just like a little dropper for like application.
Yeah, it's awesome. Yeah, no worry. Yeah.
The front tire, if you lift it up, it won't. So it's not as accurate.
Also, like the drivetrain is right there, so it has like a bike already came when it came already have like a metal plate there, right? So like it would be great if we can like take advantage of that plate, so like we can just have that housing attached to that plate. Yeah, but for the front wheel, because it's not directly connected to the drivetrain, so it doesn't have that plate. Yeah, that's also why we use it.
Yeah, thank you for you guys coming. Yeah, it's great. Thank
Yeah, sure. Okay. Yeah, the light with it's in the casing, so you have to.
you. We don't have a screen. Oh, perfect.
Yeah. Wait, yeah, there. Oh, yeah. And so like, one of the things that you're thinking about is fields, especially for the environments that we field running through. It often people will break its boat or have a problem with the wheels that's this. That's the thing they have all the time. See it, like it's in like presence. Sure. Yeah. So yeah. Is it solder? It's so if the like stops logging, it's like if just the light goes off or. So you could have like in the facing like right? Yeah. That would also means like the other condition may burn slow shading or. Yeah. That's a really has specific instances where.
if we wanted to do like a further distance, we would have to use a strong magnet. And like this other stuff. But actually the rims are almost. Yeah.
Okay, so guys, we're gonna take a few minutes here and then we're gonna start our outdoors presentation. We have like a grassy outdoor area, so we found the one right close here. We didn't want to go too far because of the bad weather, but we're outside here. We're gonna have maybe like 5 minutes break. So yeah.
You want to ramp it up? Say.
Yeah, we're really good. Yeah.
It's it at the speed. Yes. We're just gonna run the back. On the back was like everything turned on. And then we can just pick up the SD card and plug it into the adapter of the laptop. Yeah, wait, are we gonna use it for the like calibration for the data? Yeah, I think we got like the acceleration and like the speed. Yeah. Yeah, you have like the three axes. And then it's speed. Yeah. Yeah, whatever the data is right now, we'll just look at that.
First,
Okay, so
it's pretty primitive too. Well, but it's rather than it is. Probably side.
So. Just to remember, he's been here. So.
And you need.
It's a little bit. Oh, no, but stall like this. So I think stall that. Yeah. So when I talk to the it's a super cool feedback. And all fair, I just don't be interested. Yeah, what role I'm playing, you know, but I am saying it's.
So we see that to get all the way around. I could just. Well, like, for your recursions, like your grassy have the. Oh yeah, no, there's like a popular document.
Here, this little set of stairs.
It's only 4 stairs.
I think two. And then bring this. Yeah, I didn't fill anything else. I was just taking notes because it's on. Yeah. Where the competitors are like watching videos, right? Like cultural abilities.
Get a ride.
Actually, you know, like, I want to make sure that we get some real good photos before I ride, because I'm not sure if pictures of us up on a bike, because I don't know how well it's hold up. Yeah. So I just, everyone will make sure we got some good pictures.
We got some, yeah, on.
Okay, yeah.
It's been up on a lot of. And that's it. My third time here. Sorry. Did I die?
than just like spinning a thing with a drill from last year. Yeah, we'll keep turning it around. Or I yeah. Okay.
Oh, I'm sorry, I didn't see that. I didn't have it.
Wait, oh.
I don't.
Yeah, right here. Now, yeah, so I think.
Oh, wait, the dating screen. That.
Yeah, we go to the bathroom and stuff. And then I have some similar things.
I'd rather do my brother is I think that was the since earlier. The image report.
Okay. Just to look at it.
Go for it. It's
Yeah, that's really nice.
we're gonna say this. Yeah.
Okay, all right. I want to see it. I want to see it.
Yeah, that is. Or I guess I'll just hold on to it. That's easier.
Yeah, thanks.
That sounds good.
Under mine.
Oh, my boss has been here the whole time. No, she okay.
That was there. Just.
Come back. So.
So like she was asking you if so you just think so it usually it just takes in or better a they had a conference realized there wasn't going to replace it. No.
Yeah, am I right?
Oh, that first.
Also, like, it's like, actually, it's like, I think 15. Well, like, operate there. Yeah, yeah, like, I mean, it's because they're not like, so, you know. Like, one good part, you guys do that. But process it, exceed it for
1 year before what?
I mean, we're at 3.
Yeah, because of like application quality. That like impact. So.
All of it. Right. Accurate.
Where's the like? Here's one. Yeah.
Yeah. I bought one very hot. Very hot. Are you taking photos?
Yeah.
What's the name of
For someone that gets just the bike with the van.
No.
That's needs out there. Yes, Eric and I are getting the computer set up for the next thing, but I'll come up. So type just into your browser this IP address. And we're unmuted on Zoom, so it's recording. Okay, so Sophia wanted to take her picture, and then we should get rolling on the data.
Okay.
Okay. Oh. Yeah. Okay, so we're gonna start with okay. Take this.
Yeah. Very good. Right, you want to do a big review. Well, there's something. It's recording, it's all back. That's what's going. It definitely. Okay, here's where I start. Yeah. The first one is constant. I guess the middle thing is the seven. Better. I need to look through some of those. Or yes, it's good to me. Like, so when you can be it's safe like the tree. But it's really not so again. It's okay.
Okay, so I'm gonna go with the PR to a conference, and we're gonna do the judgment score times. Then we'll be back in more or less half an hour. And in the meanwhile, is going to uh, uh, personal development and like community engagement learning from the 9-1-1, especially about the community when so yeah, I'll leave it to
You want to play this one first? Hey, turn off the lights. So,
No, me acabas de sacar las clases y podemos hablar así.
yeah, we're good. Don't worry.
This project is and folks can really think however, as you collaborate with the clinicians on development community engaged learning resource programming project, it's crucial to consider the principles and criteria that will ensure high quality community engaged learning that maximizes participants' learning and community impact. At a minimum, a high quality community engaged learning experience should meet at least 4 quality criteria. High quality community engaged learning addresses a specific community interest or public concern. It includes working with and learning from a community partner. It connects and integrates community engaged experiences with educational content. And it includes structured, documented critical reflection to advance and share learning that results from the engagement with community. For example, high quality community engaged learning experience should address a specific community identified need and or public concern. A specific community identified need interest working in collaboration with a community to support access to safe drinking water by building wells, and like the Agua Clara engineering team here at Cornell, supporting the design of sustainable water treatment plants using open source technology. A high quality community engaged learning experience also includes working with and learning from a community partner. A community partner might include a not-for-profit organization, for-profit organization, a hospital, school, or a government agency looking to partner with you and your students to address a specific issue through educational outreach, advocacy, or services they offer. It's important to develop a mutually beneficial relationship with your partner and learn as much as possible from the community members you're working with. Developing relational trust and valuing local knowledge are core principles underpinning high-quality community engaged learning. Another key element of a community engaged learning experience is that the experience outside the classroom should be well integrated and directly connected to the educational content of the course or the curriculum. This means that the problem being addressed with a community partner is connected to a key societal problem or public issue addressed in your discipline. For example, a project, course, or program focused on a public or global health issue might work with an organization like a hospital or a health clinic or a not-for-profit or perhaps a government agency focused on health services or advocacy for a particular community in a specific region of the world. And the students' community engagement activities might include research, prevention education, healthcare services, or access to safe drinking water, to name a few. Importantly, your experience working with and learning from community partners should also connect directly with course content and be informed by the theories, concepts, and approaches covered in the classroom. Lastly, a high-quality community engaged learning experience also includes structured opportunities for critical reflection. Critical reflection activities that are systematic and intentional before, during, and after engaging with community ensures that participants are well prepared for examining and distilling different types of learning outcomes from their experience working with a community partner. There are a lot of different types of learning outcomes that might include new knowledge about the factors influencing the problem being addressed, or skill development, conducting research to gain a better understanding of the myriad contextual factors, cultural, social, economic, and political, that affect how a problem might be perceived and or addressed over time. Systematic and structured forms of critical reflection, such as research, journaling, weekly essays, podcasts, videos, and conversations inside and outside the classroom with peers, instructors, staff, and partners that are intentionally and strategically built into the fabric of a course or program before, during, and after a community-engaged learning experience helps ensure that the quality of the other three core elements in terms of the relevant problem focus and intervention, the level of reciprocity and mutuality in the community partnership, and the level of integration with academic content in your course or program. In fact, I would say critical reflection is the most important of the four elements of a high-quality community-engaged learning experience because it serves as the glue connecting all of the quality criteria together to form a well-designed community-engaged learning experience that is mutually beneficial for students and for community partners. Apart from these criteria, it will be important to build into your community-engaged learning course, project, or program health and safety protocols, as well as a plan for assessing student learning and evaluating community impact. The units and modules in this course were developed to support you in designing a high-quality community-engaged learning course, project, or program. Please reach out to the Einhorn Center staff for any additional feedback and support you might need.
Yes. So that's the first module. Einhorn basically requires us to sort of go through these videos and modules before you travel for your summer. Well, we don't want you to do like all the tests and all the reflection and stuff. So as you go through the videos, just like take a couple of points, a couple of ideas you can use during your summer trips and how to document your trips and how to have the best of your time during your projects. And we hope you have fun. Let's see the next one.
Defining what you and your partners intend to learn and what outcomes will result from your work is an important part of planning your community-engaged project, course, or program. It's important to consider how learning outcomes for your community-engaged learning project or course are different from the types of outcomes your community partner envisions through the partnership, and to try to align as much as possible the outcomes your partner envisions and the outcomes of the project, course, or program that you're developing. Program outcomes are reflected in how well and in what ways you've achieved your proposed objectives in areas such as project management and coordination, services provided, fundraising, recruitment, advertising, logistics, transportation, partnership development, training, relationship building, safety, assessment, and evaluation. A learning outcome is what is achieved or what results from the project or course-based learning objective. Project or course learning objectives should advance knowledge, skills, attitudes, and behaviors, or KSABs. The learning objectives should both reflect the learning you want to achieve through your project or coursework, and should also align as much as possible with the program or project learning objectives you developed with your community partner. For example, if your project, course, or program is focused on public health, then the theories, concepts, and approaches to health prevention should connect with the community-engaged learning activities, such as the experience you're having interning at a hospital or doing health prevention education in a neighborhood or local clinic. Both the community-engaged learning experience and the coursework ideally should mutually inform each other. And importantly, the course and project assignments should offer an opportunity to make those connections. Learning objectives should be appropriately sequenced, scaffolded, and developmental, and well supported over time. To draw from, for example, Bloom's taxonomy, learning objectives over the duration of the semester or the community-engaged learning experience should move from basic understanding to comprehension, to in-depth learning that entails problem solving and problem finding, along with research, knowledge generation, application, and reporting. Problems that are the focus of a community-engaged learning experience are so unstructured and complex that part of the learning experience is to identify through service and project work, along with observations, research, and conversations with various stakeholders, the multiple factors, historical, cultural, socioeconomic, and political, that inform the various sources and solutions to problems that the community-engaged learning course, project, or program is meant to address. It sounds simple, and yet not all of us have had the opportunity to reflect on how community engaged learning experiences might advance our personal, professional, and academic development. It's also likely that we have not been trained in ethnographic research, equipped with high-level skills in listening, observation, and interviewing in unfamiliar community contexts. So it's important to develop learning objectives and assignments that lead to the development of personal and professional growth or skills that enable us to engage with our senses more thoughtfully when immersed in often unfamiliar community contexts. That's what happens when you're outside the classroom. You're tapping into your senses. What kinds of interactions are occurring? What are the social and cultural norms you're observing? What do you hear people saying? What are the specific words or languages being used? It's so important to listen, observe, take field notes when you're out in a community so that later on, after the community-based experience, you can reflect on what you heard, what you saw, what you observed, and what you did to learn to adjust, adapt, and communicate more effectively. So in designing learning objectives, be sure to choose the right action verbs and the activity that represents engagement with that verb. For example, specific action verbs might be to describe the history of a particular area, to identify and explain key events, to conduct research, to collaborate with project team members and community partners, to design a health clinic or to facilitate an evaluating workshop. And consider the specific assignment prompts to examine aspects of the community engaged learning experience in connection with well-defined course learning objectives. Overall, a well-designed community engaged learning project, course, or program has clearly articulated program and learning objectives that are smart, developmental, sequenced, and scaffolded, or well supported in terms of the preparation, skills, and knowledge needed to achieve a learning objective in a community setting.
Yeah, so if we go to the next video, I'd like to probably invite Jay to tell you something about the whole goal of this. But on my side, I think the first thing when you go to a new place, first make sure you're safe and your safety is first. And then of course different communities have different cultures and they do things differently. So you don't have to necessarily know their language and know everything they do, but I think if you know one word or two words in the language they speak, that would help to sort of bring down the tension and stuff. But you don't have to know everything. You don't have all the time to do that. Maybe knowing one or two things can help you. And then finally, have fun. Yeah. Make memories and journal your days. Take photos, take videos, so that once you're done and you get back to school, you can look back and say, I had fun during my summer. So it's if you have something to add, you can add, and then you can watch the next video or something. Let's see the next video. It's a short one about cultural humility. So that's it.
Cultural humility as a learning community-engaged learning emerged as a response to the limitations of the concepts and practices associated with intercultural competence. Intercultural competence is a complex construct, and the definition, components, and attributes of intercultural competence has eluded consensus from both scholars and higher education administrators working in international and cross-cultural fields and contexts for many years. Fortunately, Darla Deerdorf, a prominent scholar in the field, conducted a study as part of her doctoral work in 2004 with prominent scholars and higher education administrators to achieve some level of consensus on the definition and dimensions of intercultural competence. And based on her study findings, the top-rated definition of intercultural competence by both administrators and scholars was the ability to communicate effectively and appropriately in intercultural situations based on one's intercultural knowledge, skills, and attitudes. Additionally, Deardorff's study found that there was a robust agreement that an intercultural attitude is a key point of departure for achieving high levels of intercultural competence. Attitudes conducive to the development of intercultural competence included the appreciation, respect for, and valuing of other cultures, and importantly, a willingness to have an open mind, to adapt, be flexible and inquisitive or curious, and developing cultural self-awareness, and both an awareness and respect for diverse perspectives and worldviews. The intercultural competence process model that Deardorff developed was intended to convey that intercultural competence is an ongoing process of improvement in terms of the knowledge, skills, attitudes, and behaviors necessary to communicate effectively and appropriately in intercultural situations. That is, it wasn't an endpoint. The right attitude, skillful and astute observations, attentive listening, self-awareness, and the knowledge of a particular culture, or even fluency in a language, demonstrates progress in learning, but it doesn't necessarily mean the achievement of intercultural competence is complete, given that each situation in any given cultural context is inherently dynamic, ever-changing, complex, and unpredictable. So cultural humility is a learning outcome, particularly as it pertains to the knowledge, skills, attitudes, and behaviors needed to be an effective community-engaged learner. Builds on and expands on the key skills and good practices reflected in intercultural competence. For example, cultural humility at a minimum embraces the ability to effectively adapt and communicate new and unfamiliar contexts, or when participating in a community-engaged learning situation with partners in another country for the first time, becoming a well-functioning project team member, or communicating in a second language, or participating in rituals that are different from one's home country in order to effectively address problems in collaboration with communities. Indeed, having cultural humility means developing competence to live, work, communicate, interact, and get along with others, and having the ability to work across difference. Additionally, the cultivation of the knowledge, skills, attitudes, and behaviors in cultural humility comes with experiences of living, working, and interacting with people who have diverse backgrounds and lived experiences, and who have developed a set of values, beliefs, and perspectives about the world that are both different and similar to your own. However, given that community-engaged learning courses and programs often require students to live and work in unfamiliar contexts and also address complex and persistent problems in resource-limited organizations and communities that have been historically driven by structural inequality, the development of intercultural competence at an individual level is a necessary but insufficient condition for building supportive, more just, inclusive, and healthy relationships, and the collaboration necessary for achieving the goals and maximizing the sustained long-term impact of a community-engaged endeavor. Hence, while the development of intercultural competence is necessary for adapting to new and unfamiliar communities or contexts, intercultural competence is insufficient in community-engaged learning contexts that require learning how to question, challenge, and resist rather than adapt to unjust cultural norms, rituals, and policies, or practices and institutional arrangements that have historically caused harm to certain individuals and groups. Cultural humility and community-engaged learning, therefore, is an important learning outcome that entails the cultivation of knowledge, skills, attitudes, and behaviors necessary for taking action and challenging harmful aspects of the status quo, often necessitating the transformation of how we see ourselves and the world around us.
Who has something to share with the rest of us? Maybe you've traveled to a different country or you've done some projects in some different places, which is not like necessarily your home, and you have like something from that experience that you would like to share with the rest of us. Any volunteer? If you've done like let's say community engagement or done a project in a place that's not your home and you'd like to share with us your experience in that community or with the people you met there, you'd like to share something there. You first and then. How did you like the experience? Did you like the experience or? Fully prepared for your busy? Did you have like an encounter where you felt like you were not prepared for this? And on the other side, did you think thank you, thank you. I what's your name? Okay, yeah, thank you for sharing. So yeah, I think when you go like out the community and your host will be like your host probably will be the first like and most like close person to you before you get like to the community. So make those bonds, make those connections, and live your life. Have some fun. Let's see the next one, and then
If intercultural competence is an important learning outcome that serves as a precursor to the formation of cultural humility, what then are the key dimensions of cultural humility as a learning outcome in community engaged learning? In the context of community engaged learning, there are three core dimensions of cultural humility that can be framed as learning outcomes. One is the ability to engage in self-reflection on one's identity and positionality as it relates to others. So to have a robust self-awareness. Two, the ability to adapt and communicate effectively in diverse cultural and community contexts. And three, to cultivate the knowledge, skills, attitudes to recognize and challenge unequal relations of power and to enact cultural humility in different spaces and places on different levels, individually, interpersonally, institutionally, as part of a larger system. Thus, in order to better understand and more effectively communicate and build relationships with the communities we work with through community engagement, we have to first understand ourselves and develop self-awareness. The first step in the development of cultural humility is self-reflection aimed at exploring the various dimensions that make up our unique selves and identities, who we are, where we come from, our values, personalities, beliefs, affiliations, interests, and explore where all of these attributes and the meanings we attach to them represent ourselves and identities at particular points in time and in various contexts. Understanding our identity and the identity of others is quite a challenging learning process, given that most students and people in general have never had the time and space to reflect on the complex nature of who they are, not to mention how challenging it is to reflect on our own assumptions about who we are with our own set of assumptions, given that we're inherently biased. Reflecting on our assumptions of who we are, ourselves, and our identities, and the sources of those assumptions is a complex endeavor that requires an open mind, a willingness to examine distorted or false assumptions we might hold, and a comfort level with ambiguity, given that our identities are dynamic, always changing and evolving. As a preparatory activity, it's important to intentionally structure exercises that include identity exploration with students early on in a community engaged course or program, particularly because they likely have not had an opportunity in their prior educational experience to engage in self-reflection, nor have they had an opportunity to better understand the identities of the students they share the classroom with, and how each have experienced a world around them based on their identities, the good, the bad, and the ugly, in terms of their ability to be who they are in any given context. In addition, identity exploration as a preparatory exercise is important given that community-engaged learning takes place outside of the familiar context of the classroom, often outside students' frame of reference, and sometimes outside the boundaries of their comfort zone. Such experiences can cause students to experience what I like to call different types of dissonance. The different types of dissonance that students experience that result from community engagement in unfamiliar contexts acts as a catalyst for students to critically reflect on similarities and differences that they're observing between the culture, norms, rituals, practices, and belief systems that are familiar to them, their previous experience, and often surfaces false or distorted assumptions they hold about themselves, others, and the world around them. Community-engaged learning experiences in this sense, they offer students in-depth rather than surface-level opportunities for significant personal growth, learning about themselves, and ground-truthing what they know about their peers, each other's experience, the stereotypes they may hold about each other, or the communities that they'll be working with, and to find ways to appreciate each other and the communities they're planning to engage with. This means engaging students in activities, including the Identity Pie activities shared in this module, to critically reflect on, describe, and explain what it means to be who they are at this point in time in their life. They should also be able to attribute deeper meanings to various elements of their identity. They should be able to determine which aspects of their identities are part of a subordinate or systematically a disadvantaged group, and or a dominant, systematically advantaged group in specific contexts. As preparation before engaging with a community partner to address real-world problems outside the classroom, it's important to develop community inside the classroom with their peers, doing identity work, such as the identity exercise, which asks students to reflect on, construct, and share key aspects of their identities with others, which allows them to gain a deeper understanding of the meanings they attribute to their own identities and those of their peers attached to their identities, often for the first time. And it serves as a first step toward building a relationship and cultivating community in the classroom. Most importantly, identity exploration with one another offers a meaningful opportunity to build a more supportive, just, inclusive, thriving, and healthier community inside and outside the classroom. For students, this type of learning process will seem counter-normative to the competitive, sometimes superficial nature of the relationships students are accustomed to and their daily classroom experience. Having an opportunity to unpack our biographies and share aspects of our identities with each other in the classroom, seeing similarities and differences in your peers, and to learn more deeply about each other's individual interests, vocations, families, group affiliations, their personality types, places they come from, religious beliefs, and a number of other important aspects of their identities and biographies is counter-normative to their ritualized and often taken for granted experience in classrooms throughout the day. And it goes a long way toward building a supportive community as preparation for community engaged learning, since it may very well be that they will be engaged in community-based projects with each other later on in the semester.
We have a few more. I don't know if they're done, but I don't think.
because I think they're coming back in a few minutes. 3.5 hours. Yeah, that's fine. Yeah. All right. We'll just take a short break. They should be coming back in a few minutes anyway. So, I think when they come back, we're gonna do scoring, data viewing, and then we'll be wrapping up. So, yeah. I guess if you want to wait, there's some fun things in this hallway actually. I think sorry, Cornell Lion Dance is practicing right there if you want to see that. There's also some pretty cool displays down the hallway of like some history of Meki stuff that was made at the school on like kind of like museum style. So if you guys want to look it down the hallway, it's pretty cool. Yeah.
Perfect. The first time was like
Thank you everyone for spending your Saturday with us here at Upson 116. These are a few closing remarks as we finish our competition today. So I'm just gonna go over a summary of the event, how this summer will go, and then insights onto next year and our future vision for Gaia. So, summary, we were able to maximize the positive impact that we have in communities by empowering college teams, UCSD and Cornell, to conceive, design, prototype, and execute their solutions for global sustainability. So this is a timeline of Gaia and a few key events that have happened for our org. We were founded in 2022. Then we had our first Peru trip 2 years after. Last year we held a competition with the Cornell team, one team, but it was a demonstration of technical designs, Peru this summer, and then today, the competition. So these are the overall scores. This is my first time looking at them as well. So Cornell got 47 points for design, UCSD 37.5, and then prototype, Cornell got 37, UCSD 0. So these graphs, I'm not sure. I think they're
I'll go through them. So this is a little bit just so long up there in the judging, but this is the data that we were able to plot from this basically last 20 some minutes of the CSV file. So you can sort of see 3 chunks of data, especially in the accelerometer. And so the first chunk on like the left half is when Chris was writing. The second chunk on like the middle right is when I was writing, and then there's a smaller pause, and then on the far right is when Daniel was writing. And it does look like the Hall effect sensor did not function for my ride or for Chris's ride, but I guess luckily, good thing that we kept riding afterwards, because probably when you guys were adjusting the tape, that might have somehow gotten a wire that perhaps had wiggled out of the Hall sensor back into shape. And so then we start getting some RPM data towards the end, although there are still some periods where it's cutting out. And so that's what contributed to like the partial score on the Hall effect side. And then there's still some work to be done on the acceleration. Do all the axes make sense? But at least we are seeing spikes that seem to vaguely correspond with when we were riding, when we were like going over the curbs. And so that's good. There may need to be some orientation shifts or some CG adjustment. And oh, I guess we forgot to fill in the ABCD while we were up there, but we can take a minute to just go through some points of feedback for both teams. If you do want to start with that.
Oh, yeah, I mean, I guess one thing I'd say that Cornell team, I thought you did a great job of kind of scoping yourself for obviously what was going to be realistic and yeah. At some point, you might need to say, hey, this is prioritized. Want to try to, if we think this is achievable, let's try to execute. That you guys did a really nice job on that. I thought were good for someone who isn't very well versed in electronics, like maybe I could speak too much to that detail, but let's say just being able to step back and really just kind of just give the output rather than getting into too much detail, but you'll have a report to be able to. Yeah, also, I think a really great job with doing some prototyping, I think with, trying different mounting points and again, fail faster, just try stuff, Take some things on there, see what works. I love the conversation about sitting, that one night just playing around with things, driving around, and seeing it holds on. Those, I can't tell you how valuable that kind of experimentation. Just get in there, even if it's something crazy, right? Well, put two changes like this, just kind of crazy. Let's try it and see how it works. So, I guess those are. Not what I'm gonna say, so. If I got anything else, I'll add it on. Yeah, thank you.
And then I guess on that note, we'll also do more like official feedback to show you guys the full rubrics, and we'll send that out like after the competition and when we can like get them a little bit cleaned up. And also as you make your like written report version, also be able to offer feedback. And then on my side, some feedback that I had was, I think UCSD, especially as a new team who was both in this point of time, not only attempting the project, but attempting to like form yourself from essentially nothing, that was really impressive. And I thought on the electrical side, I liked that you guys were thinking about connectors, for example. That was an area where I think UCSD had like a more put together proposal on the connector side than the Cornell team. I do think I would echo what Chris was saying on the scoping. That's kind of why we gave you the prioritized order of sensors. So even though, like, yes, ideally we have them all, and so if you're seeing like, yeah, we're a brand new team, it's going to be hard to pull it all together. Works is better than 6 is. And then some other things on the UCSD team, I think would be good to think about in the future is more defense of exactly why you're choosing a particular there was sometimes some going back and forth on like, well, we thought about this one and we thought about this one, and a little bit of explanation on why the different things were tried, but not necessarily a clear path of our decision-making process. We tried X, Y, Z, and then arrived at this through this. I think there could be cool. And then on the Cornell side, excellent job at keeping the costs down. I was honestly surprised that you're able to have a system with under $100 price tag, even for the components that you weren't able to like get on the bike. And then surprising that the torque sensor, the drivetrain torque sensor, as the number one priority, was the one as like some conceptual difficulties with that one. But in the future, I'd also love to talk about like these getting comments. And I think you guys had a good use of bringing in the equations that showed you understood how the sensor is actually operating, without like filling the slides with math. So for example, the strain, and the strain gauge factor. Shows your understanding of how the strain gauges work. And use of the LT spice simulation, on the one hand, props to you for like knowing how to use LT spice, but also that is a resistor divider. And so that can be done with algebra and doesn't actually require any sort of simulation and might be just with like the one level equation for the resistor in the future and like give more intuition without having to like report the solutions. Yeah, neither chain it seemed like ended up going very deep. The more I was gonna say confident, that's not the right word. The more signal processing side of sensor selection, and thinking about what should be then precision, accuracy, filtering, the stuff that was in like the technical lecture, what should those be? And so also be like a way for both teams to sort of level up in the future is to get that additional level of we're not just picking things that will work when we put them together, which is like a really important aspect of it, but also being able to predict if they work when we put them together and when we look at that data, will that data actually and yeah, overall, really great job. Thanks.
Yeah. But that right? On that both groups, both I think, especially for you folks who didn't have a prototype with you, it takes a lot to get up there and illustrate an idea. Like myself doesn't spend a lot of time and I'll spend a lot of time off that. And I still understood, I came away understanding what you guys are working on. I had questions were in both the inner minutia of the questions that you would ask about update you guys from a user perspective and how did you need to adjust it, how did you make choices that not only are we achieving the goals that we have set out for this project, but at the end of the day, the person throughout high school is passionate. Yeah, really. Hopefully. Really impressed with the illustrations and the typing there. But I was still really impressed with the ability that you guys had to illustrate for some maybe very thinking what you were trying to solve for, how you approach the problem, and maybe it's so important at it. Good luck with the rest of your studies, the rest of the projects we're really excited for my business card is over there on the table and we could get in touch with me in Chicago if you're ever in town on my ever visit.
Thank you to our hosts. Thank you, Becca. Thank you, AJ. Thank you, Sophie, right?
Yeah.
Okay. Thank you very, very much.
Echoing on that feedback, having been a part of Gaia since the beginning and seeing how much it has grown, it's beautiful that now we have people coming from my hometown. I mean, and then Cornell, I'm really, really happy with how today went. And you guys did an amazing job. I am so proud of everyone who's here. Thank you, WBR, for coming. Um, yeah. Summer plans, trip location and dates to be determined, but it's going to happen. And we're really excited to share those details with you guys in the coming weeks, month. So keep in touch with us, and that'll get out. Next year, we would like to expand competitors. So this is where you guys can come in and help us, students. UCSD, Cornell. If you guys have friends that go to other universities who are engineers and who are also passionate about Gaia and our mission and our goals as an organization, please, we will reach out to you after this competition, but we want to grow GAIA competition. So hopefully next year when you guys come back and compete, we have other schools and it can be more rigorous competition. So yeah, look for a message from me and the marketing team soon. Our vision for 5 years is, as I mentioned earlier, get more competitors. We'd also like to expand our org of organizers. We're quite small and we're looking to keep Gaia for many years after I graduate, Becca, AJ, after all the leads graduate. So Cornell, spread the word. You see, everyone spread the word, spread Gaia. On that note, can you guys all take out your phones right now? Oh, wait. And go to Instagram. Type in Gaia, GAIA underscore competition. GAIA. Sorry, my bad. Gaia underscore competition. And follow our Instagram account. I did do an Instagram takeover today, and a bunch of you guys were posted on the Instagram and will be posted on the Instagram from the photos and videos and content from this competition. We want to show you guys off. Everyone, we're so proud of you. So make sure to repost our posts on your story, keep up to date with what we're doing as an org, and connect with us if you ever have any questions. Thank you, WBR. And these are a couple of our sponsors: Cornell Engineering Leadership Program, Einhorn Center, ECO, C Lab, and that is all, I think. Yeah, congratulations to both our teams. Okay. And I hope everyone has a great day. Enjoy the rest of the evening in Ithaca. I sent the UCSD team some recommendations for where to have dinner. So enjoy your evenings. Thank you.
Lost in the conference. I don't think I were even if you're trying to pare back a lot, but if you have, you know, like still 500 things, got I, you know, and
One of the books is all of the people just like you're like sleeping. like leaders or something like that.
Yes, yeah, I think now everybody's in China. But
Yes.
they will be back. It's there.
No, no.
I have the privilege. Oh,
Because we so like under a lot of things this was a very play that's the very the water out of us. Like teal going everybody so we're turning about long in the summer. We're going to try to make pulsing and outlets. Like there's like we can start working with pulsing straight area. Straight. So like I did having like a ball like a lot of balls.
Scoping, like, okay, what he has. What if you're getting into this? Because now I have the files. I think we sound
Bill, we're going to be working on what we run years. It's fine. There's so much uncertainty. It won't. So, and whether or not it's going to get, whether or not it would be the opportunity to go on there with other tracks so that when the kids need to be folding together and then like,
yeah.
So hopefully on schedule that meeting, and I think keep following up with John. So John is pretty much the one driving this. And it's engineer. Really Andy's the one running that particular project. So they'll
Yeah. Yeah. I guess like with you guys, I would love something not just like just like just like yes.
About future, yeah,
Like I did my last one, but probably hard plans. Yeah, so that's so all you guys do something things on the youth bag. It's what we did from problem. Yeah. So
so do you have any volunteers with them? So why it's going on with them?
It's more like they reach out to us before.
So, which is so but we're still get the family it's very specific. This
Yeah, I guess. Well, that's really, like, I think, one of the things our development group is a lot of the alternatives, and they are doing something with one of the German universities, like out the plans.
Like from so obviously it's has to be like, there's like something like that. Like we don't want to like actually use like this center street back to make sense. But it's like
Yeah, successful.
A project that we're working on now right there. I think they're right now, understanding, using that for developing a laptop. So those are the next steps. That's the other. Yeah, no, appreciate it. It's a great experience. It's always just like the beginning of a relationship about seeing.
oh wait, Sophia, you should take everyone first. Yeah.
Okay, I don't take a group photo. So if you guys can all please make your way just outside right here. Uh, this is
Yeah. Hopefully, they're very good thing, but yeah.
Good luck, everyone.
Yes, thank you.
That's what I think is really interesting to see that's the issue.
Yeah.
You can't get.
It's feeling pretty like big. It's right. Yeah. Where's it at? Next time you got one? Okay. Get that. Oh, I don't know. What were you?
Well, so small, right? I've never seen it. And it fits right